Okay, so hello everyone. Thanks for attending our tutorial on physics-based differentiable rendering. So today, my name is Shuang Zhao. I'm an assistant professor at the University of California, Irvine. Today, I'm happy to offer this tutorial with Yanis from Carnegie Mellon University and Sai from MIT. So without further ado, let's get started. And here is an outline of this tutorial. High-level one, of course. So we will start with a high-level introduction on physics-based differentiable rendering. We'll discuss a number of aspects related to what we can do, what we may not be able to do at the moment, etc. We'll also go over a few common misconceptions related to physics-based differentiable rendering. And then the second component of our tutorial will be a high-level description about modern or state-of-the-art differentiable rendering theories and algorithms. Since we don't assume you are all kind of rendering experts, so we will keep our discussion relatively high level. But on the other hand, if you are interested in knowing the details, we will have the pointers to papers or other materials in case if you are interested in knowing the details. And the third component of this tutorial will be differentiable rendering systems and applications. So we will again go over some existing systems. Some of them are still under development, and also show certain applications that we have done with those systems. And finally, in the end, we'll have a Q&A session. So in case of questions and interactions, we plan to mainly use the Zoom chat. So if you have any question, feel free to just type in there. We'll try to answer them during the tutorial and of course in the very end as well. So if you have any question, please feel free to just type them. We might not answer them immediately, but we will try to cover all of them if we can. Okay. So let's start with the introduction. So first, just in case, if you're uncertain what differentiable rendering means, it's basically about, instead of generating an image, which is what forward rendering do, differentiable rendering instead estimates the derivative or gradient of each pixel value with respect to some abstract parameter or some arbitrary parameter. So in this example, as you can see on the left, we show a forward rendering result, which is a nice indirectly lit dining room with the main light source being the sun outside. On the right-hand side, we visualize the derivative image, and this derivative is calculated with respect to the location of the sun. So again, this is just a small example of what differentiable rendering is trying to compute. In this example, we're not trying to solve any inverse problem or anything. Okay. So you may wonder why bother kind of generating such weird looking derivative images. A main reason why differentiable rendering has become a kind of an area that received a lot of attention is because these techniques can be used to solve inverse rendering problems, or sometimes known as analysis by synthesis problems. Basically, what these problems do, or what these problems focus on, is to infer scene parameters based on input images of the scene. Scene parameters include, for example, material parameters like surface albedo, and also things like camera pose, and even the shape of an object. So these can all be, say, categorized as scene parameters. And input is images of the scene. So you can imagine this is a kind of central problem in computer vision, because it's related to, say, 3D reconstruction and so on. But not only that, differentiable rendering can also be useful for integrating forward rendering into, say, probabilistic inference and machine learning pipelines. As you can imagine, many advanced or modern machine learning models, at least when being trained, has certain things like rendering loss. So to backpropagate to backpropagate the losses during the training process, you need the forward rendering module to be differentiable. So this is the second reason why differentiable rendering can have a lot of use. So as a result, because they can be used to solve inverse problems or develop new machine learning or probabilistic inference pipelines, they have lots of applications in vision, graphics, say computational imaging, and so on. Okay. So let me give a kind of more visual demonstration of forward versus inverse rendering. So again, in forward rendering, we take a number of scene parameters. Here we write as theta. In some of our later slides, we might refer to scene parameters as pi as well, but they are actually, we mean the same thing. So scene parameters include scene object geometry, material properties, lighting information, everything. So forward rendering takes all these information and then generates a rendered image for it, which is shown on the right. Okay. So inverse rendering is basically the opposite. If we take the right image or a number of images, if needed, can we infer the scene parameters out of those images, right? That's basically one of the classic computer vision problem. So here we treat it as an inverse rendering problem. Okay. So before diving into a lot of details on inverse rendering, let's go over forward rendering a little bit, because you cannot really talk about inverse before having a good understanding about what forward does. Of course, since this is not a course about, say, 3D rendering in graphics, we'll stay relatively high level when talking about forward rendering related techniques. So commonly to render an image, there are two categories of techniques. The first one, which arguably is the more kind of traditional one to some extent, is rasterization-based methods. So these techniques relies on rasterization that used to be the kind of gold standard on, say, graphics hardware, and of course are used by many, if not most, say, computer vision pipelines. So that's one type of commonly used techniques. However, there's a second class of methods, which is ray tracing, which are ray tracing based. And these techniques are used more often in physics-based rendering, as we'll discuss later. So before talking about ray tracing versus rasterization, let me first try to kind of define what ray tracing is, just in the context of this course. Because unfortunately, ray tracing is a term that has been heavily abused. So it can mean many things actually right now. So just for the context of this tutorial, again, we use ray tracing to just mean one thing, which is ray surface intersection computations. So, okay, for example, we don't use ray tracing to mean anything like path tracing or some other of the Monte Carlo step. Here we just use ray tracing to refer to the elementary ray surface intersection operation. As you can imagine, ray tracing is applicable to both explicit, such as a mesh, and implicit, such as a signed distance function surface. Because in both cases, for example, for the mesh case, you can, it basically boils down to ray triangle intersection, which can be solved pretty efficiently. In case of an SDF, you do things like spherical tracing, and that can also tell you where the ray intersects with the surface. So we will use ray tracing to basically refer to this specific operation. So under this definition, we can see that ray tracing is the basic building block for most, if not all, physics-based rendering algorithms. These include path tracing. We'll talk about it a bit later when we discuss how to handle things like global illumination, and even more advanced ones like bidirectional path tracing and so on. So with ray tracing properly defined, we can now talk about physics-based forward rendering. So if you have taken a course in like graphics, you might have seen some algorithms in this category. Most of them rely on Monte Carlo because you have since you have to solve, for example, the rendering equation or the path integral, both of which we'll talk about briefly later in today's tutorial. But these methods all rely heavily on Monte Carlo, which basically means you have to randomly sample either some directions or some passes and then kind of average out their contributions. So that's the high level style of most physics-based rendering algorithms. And we'll discuss how they can be differentiated because we know how to do that now. So the benefit for having physics-based forward rendering is that these algorithms can capture pretty complex light transport effects, including soft shadows, interreflection, subsurface scattering, etc. So as an example, here we show a rendered image of 4 materials, well, of 2 soaps, olive oil, and a type of wine and milk. As you can see, as long as you have an accurate model to begin with, fairly high quality results can be achieved. Okay, so that's about forward rendering, but of course, as in computer vision, people are typically much more interested in solving the inverse problem. So in which case, again, as we mentioned just now, we take rendered images or photographs, if you deal with real data, we take images of some scene, and the goal is to infer some or all, I mean, normally some scene parameters, such as, again, surface albedo, geometry of an object, etc. So when talking about physics-based inverse rendering, the goal is to invert, again, of course, physics-based forward rendering, which means we want to invert the many complex light transport effects, including, say, soft shadow or even interreflection and subsurface scattering. The reason why we want to do this is because the ability to invert such complex light transport scenario is important to many applications. The first application, as I mentioned earlier, is the fairly classical shape and the material reconstruction. So basically, if we take a bunch of photos of an object, we want to basically build a digital model out of it. Again, it's super classic computer vision problem. But fortunately, thanks to the recent progresses in differentiable rendering, we can now solve this type of problems with much higher complexity and with much higher reconstruction quality. Actually, this figure is from one of our recent works, and I'll go over more details about this work when we talk about systems and applications. Another type of application that kind of requires complex light transport to be handled is actually computational fabrication. These days, we have fairly sophisticated colored 3D printers that you can, for example, control how you mix different types of inks at each voxel, basically during the printing process. So naturally, the question becomes, how can we determine all this type of mixture information or material configuration so that we can reach some desired final appearance? So this becomes a inverse rendering problem where things like subsurface scattering has to be considered, because normally these printed materials are not 100% opaque. So if you neglect all the subsurface scattering, the printed appearance will not match your desired target that well. And the third type is physics-based learning. This is, I briefly mentioned, this possibility of integrating physics-based rendering into, say, machine learning pipelines. We do have a recent work on this as well. So in this case, we try to invert scattering. So the goal is to predict the subsurface scattering parameters using a network. So when training this, we basically replaced a traditional decoder with a differentiable renderer so that we can train an encoder by, say, end-to-end differentiate or back propagating the training losses through the rendering steps. So in the end, we get a encoder at testing time that can be used to predict scattering parameters. Again, Yannis will go over this example later when we talk about systems and discussions. Okay. So you might wonder, since physics-based forward rendering has been studied in computer graphics for, decades, and we have got very sophisticated solutions for that. So you might wonder, why is differentiable rendering hard? Is it supposed to be just say autodiff some forward renderer? But it's not that simple. So let me explain. So the first, in principle, what physics-based differentiable rendering does is to differentiate solutions of, let's say, the rendering equation, which by itself is an integral equation. So given the complexity of this equation, differentiation becomes non-trivial. And also the relation between the solution of the rendering equation, which is basically your light field, your radiance field, and the scene parameters can be highly complex because very often these type of relations are nonlinear. So this is one challenge. The second challenge is that in many practical applications, as we will discuss a little bit when talking about applications again, it requires handling very large gradient matrices because you can have, for example, a rendered image with 1 million pixels, and you can certainly have 1 million parameters as well, because you can, for example, optimize the pixel value of a texture, for example. That gives your final gradient matrix a very large number of entries, like 10 to the power of 12. You cannot even possibly store everything. So this can cause some challenges. This will not be the main focus of our tutorial, but I will give some high-level discussions later as well. And another thing is that physics-based differentiable rendering can be tricky to implement correctly. Again, as you will see, hopefully, after completing this tutorial, just simply auto-diffing a, say, path tracer can very often not work. And we'll explain why later as well. So again, this is what I just explained, handling many parameters. So in practice, the forward rendering function I is actually factor valued because you need one value per pixel, right? You are normally rendering an image with many pixels. And we can have many scene parameters as well. So then the gradient matrix can be super, super huge. So this is one big challenge when developing practical differentiable rendering algorithms. Fortunately, we do have some new techniques that addresses this challenge. Another thing, which will be the main focus of this tutorial, is that precautions must be taken to ensure correctness. In other words, if we just take an over-the-shelf path tracer and just apply like whatever PyTorch autodiff to it, it may not always work. It can work sometimes, but not always. So why it might not work? So there are a number of details that has to be handled correctly for getting correct gradients. One example is that for example, in a path tracer, as I mentioned, most forward renderers use Monte Carlo, which basically means it has some random process. It also has to compute the PDF, the probability density function related to some random sampling process. So very often you run into the question of, should the probability density function be differentiated? And the answer is actually quite complex. It can go either way. Yanis will discuss this a bit later. And another big challenge for dealing with especially geometric differentiation is discontinuities, which basically means if you just do autodiff, that corresponds to differentiating only the integrand of the rendering equation. Remember, the rendering equation is an integrated equation, so it has an integrand there. Only differentiating the integrand is not sufficient either. And again, this will be one of the key points that we go over in today's tutorial. Another question that people might wonder is, why not just do finite differences, right? Because as long as you can do the forward simulation, finite difference can give you some reasonable gradient. Unfortunately, the answer is yes in theory, but really no in practice. Because finite differences has a number of problems. The first is that whenever you use finite difference, you need to determine the spacing epsilon. However, if you use a large epsilon, you get high bias. As we'll see later, high bias is bad. However, if you use some very small epsilon, you can run into rounding errors. You can also run into having Monte Carlo noise to explode. Because remember, your R function here, when you do physics-based rendering, can be non-deterministic. So you can have Monte Carlo noise. So if you divide R by some very small epsilon, it basically makes the noise can make the noise to explode. And there are some other details when you have to correlate Monte Carlo samples when you compute the differences. And most importantly, finite differences scale poorly with the number of parameters, because you have to do at least one subtraction per parameter. So imagine what happens if you have 1 million parameters, right? You cannot possibly render 1 million pairs of images. So, well, you can, but it's going to take forever. So all these reasons make finite differences really not a really practical solution when dealing with, say, physics-based inverse rendering problems. Another question you might wonder is, do we really need global illumination? Can we just use some very simple forward rendering model so that it can be differentiated easily? The answer to this is that first, global illumination, we now can simulate them with state-of-the-art differentiable renderers, which is good news. And also, global illumination such as interreflection is actually required when solving many inverse rendering problems, including computational fabrication, as we just mentioned, since we have to deal with model subsurface scattering. That's one type of global illumination. And in many non-line of sight scenarios, we have to deal with global illumination as well. So really, at this point, since we now can do it, we should try to do things properly. And also, we have the systems that allow us to apply proper, say, inverse global illumination, so that we can solve many applications like the 2 examples shown here better. And again, we'll go over some of the applications later in today's tutorial. There's another aspect that I want to discuss briefly here. Since this is something we feel that is very often neglected in many, say, analysis by synthesis techniques in vision, which is about pixel level so-called anti-aliasing. So this is the kind of the story. If you don't do anti-aliasing, how you compute the pixel value is just by evaluating, again, under the ray tracing framework. You trace a ray through the center of a pixel, let's say XC here, and then you just compute whatever shading there. That gives you the pixel value. But if you do this, if you just sample a single point within a pixel, you can run into aliasing as the one shown on the left. And there are many other problems as well, which I will discuss a bit later. Another way to compute pixel values, well, when you have perfect anti-aliasing, is to actually calculate an integral within the pixel. So instead of just grabbing the basically incoming radiance through the center of the pixel, you're actually averaging the incoming radiance through all points within the pixel. This does not only give you a smoother image to look at, it can actually have a bunch of other benefits when solving inverse problems as well. For example, as you can imagine, in this simple case shown on the top, when the I function, the shading is binary, if you don't do any anti-aliasing, then your final image will be binary valued, either 1 or 0. However, if you can compute the proper integral over the pixel, you get a continuous valued image. So why is this useful? Because when you have a continuously valued image, you get more information. And also the image becomes more differentiable, because as you can imagine, if all you get is a binary image, you cannot get any useful gradient out of it, because I mean, differentiating a binary value always gives you 0, right? However, when you differentiate an integral that gives you the pixel value, that's perfectly differentiable, so which can give you much more information. As a result, by applying anti-aliasing, we can get more robust inverse rendering optimizations. So this is something to be aware of when, for example, applying differentiable rendering in virtually any application. Another thing that I want to discuss briefly is geometric representations. So here, we have two examples, either explicit geometry like polygonal meshes, or implicit geometry, such as like sine distance functions. This is another benefit of ray tracing compared to rasterization, because for rasterization, you cannot easily rasterize implicit geometry unless you convert it to explicit first. However, ray tracing based forward rendering is largely agnostic to geometric representations, because as long as you can compute ray surface intersection, such as using spherical tracing, then for the rendering, forward rendering doesn't really care whether you have a mesh underneath or you have a SDF underneath, which is a very nice feature. This situation actually becomes more complex for differentiable rendering, which we will discuss a bit later. So the high level reason is because differentiable rendering requires handling discontinuities, and discontinuities of implicit geometries are actually harder to detect. Okay, so that's my part of the introduction. If I don't see any questions in the chat. So next, we'll have Yanis to continue our discussion.
All right, thank you, Suang, and hello everyone, and thank you for joining our tutorial. So I'll continue the introduction by going over a few reasons why we think that people should really start using ray tracing based differentiable rendering. And again, to clarify terminology here, by ray tracing based differentiable rendering, we mean all types of differentiable rendering that use Monte Carlo integration, and also ray tracing is a core element to perform intersection and visibility checks. And for that, I want to contrast ray tracing differentiable rendering techniques with rasterization-based differentiable rendering techniques that are very common in computer vision. Many of them have appeared in the last 5-6 years. There are very actively maintained and actively used packages that implement differentiable rasterization, and a lot of papers use them for a variety of applications. So why do we advocate for using switching or considering switching to ray tracing based differentiable rendering? So the first reason has to do with the fact that ray tracing methods are not slower than rasterization. So a common misconception within especially computer vision, the computer vision community is that ray tracing based rendering techniques, both forward and differentiable, are very slow. Now, especially when we consider direct only illumination, which is the setting where rasterization renderers are limited to, ray tracing techniques can actually be competitive a lot faster than rasterization-based differentiable renderers. And this is in large part because of the fact that ray tracing operations and other integral operations for physics-based forward and differentiable renderers have now become available on GPUs, for example, the NVIDIA RTX system. And not only that, but it's also important to take into account that in any given inverse application, visibility checks and intersections and other operations, some of the most common, operations that make up for the biggest part of the computational payload of a ray tracing based technique may not be the actual bottleneck. So let me show you an example for this. So this is a comparison based on a paper by Luan, Fujun Luan and Shuang and a few other colleagues that Shuang will elaborate on later in this presentation, where we're looking to optimize a mesh, starting from the initial mesh shown to the left and to optimize it to match a target image to the right. We can do this optimization using either a ray tracing based differentiable renderer, in particular a renderer called PSDR CUDA that's all implemented on an NVIDIA Titan RTX, or we can do this optimization using PyTorch 3D, and in particular the soft rasterizer differentiable renderer. And this is an optimization that involves tens of thousands of vertices. It's a high detailed mesh. So as I show here, performing one rendering operation can actually be a lot, differentiable rendering operation to be clear, can be a lot faster using the optimized PSDR CUDA implementation, 2.8 milliseconds, than using the rasterization-based implementation on PyTorch 3D, 52.5 milliseconds. So for problems such as this, direct illumination problems, even situations where you are solving for a lot of parameters, ray tracing-based techniques are not only not slower than rasterization-based techniques, but can actually be competitive with them. And the other thing to take into account is that when we are solving this kind of shape optimization problem, there are a lot of other computational operations one needs to perform, such as backpropagating through the image loss, and most importantly, handling meshing topology issues, propagating vertex gradients correctly, remeshing, and so on. And all of those are actually what make the bulk of the computational time. They're the real bottleneck here, rather than the rendering time. So it's using ray tracing based differentiable renderers, it's perfectly plausible nowadays perfectly feasible nowadays to solve these very high dimensional optimization problems that often people think are only feasible through rasterization based differentiable renderers due to performance issues, as shown here. Now, not only are they not slower, in fact, they're competitive. Ray tracing-based differentiable rendering methods offer another advantage compared to rasterization-based differentiable renderers in that they compute correct, unbiased gradients. And what I mean by that is that the ray tracing-based differentiable rendering techniques can accurately handle all of the different types of discontinuities, visibility, and so on, tricky effects that show up even when one only considers direct illumination. So I'll go into a lot of detail about what I mean with these visibility discontinuities and other issues that show up when differentiating direct illumination. I will simply say here that these are the kinds of effects that often rasterization-based techniques have to approximate. They have to smooth, for example, use smooth visibility, resulting in gradients that do not exactly match the correct rendering model. And you may think that smoothing visibility actually doesn't matter. You can just get a good optimization using that. But as far as optimization goes, actually performing optimization using correct gradients can have a pretty big effect into the final optimized result. Okay. Let me just say one thing. I saw somebody posted a question in the chat. I'll try to answer all questions at the end of this section in a few minutes rather than while I'm narrating. But please feel free to post questions in the chat and I will get to them every 5-6 minutes. So going back to this example, here for the same inverse rendering problem I was showing earlier, if we run it under identical optimization settings using accurate gradients computed using ray tracing based differentiable rendering, we get a much more accurate result than if we perform optimization using the approximate gradients obtained using Python 3D. So not only can we do faster than rasterization, or at worst at about equal time, but also we can do a lot more accurate optimization, even in the context of direct illumination. Excuse me. Another thing I want to mention here is that outside of direct illumination, and this is something that Shuang mentioned earlier, ray tracing based techniques can allow us to handle complex light transport effects, something that is out of reach for rasterization based differentiable renderers. So we can handle soft shadows, environment illumination, environment maps, inter reflections, scattering, caustics. All of these are effects that fit naturally and generalize very easily into both the ray tracing based forward and differentiable rendering paradigms. And lastly, in addition to providing us with generality in terms of light transport effects, ray tracing based methods also provide us with generality in terms of other scene parameters. For example, parameterizations, different types of BRDFs, different types of shapes, very importantly, such as point clouds, explicit shape representations such as meshes, or implicit shape representations like neural SDFs, neural occupancy networks, or even the non-neural variants of these implicit surfaces. And they also give us generality in terms of the types of cameras we can use. So if instead of using a standard intensity-based camera, you're using a light-filled camera, the camera takes into account polarization, time of light, hyperspectral effects, and so on. All of these are types of measurements that we can easily handle with ray tracing-based differentiable renderers rather than, and we cannot easily handle with rasterization-based differentiable renderers. So in the second part of this tutorial, we'll provide a lot more detail about the top 2 points. First, what exactly we mean, what exactly is needed to do correct differentiable rendering, and algorithms and systems for implementing these differentiable rendering algorithms efficiently using ray tracing based techniques. And in the third part of the tutorial, we'll go over a few applications where ray tracing based differentiable rendering techniques have found applications that involve complex light transport effects and other more general scenes, for example, different types of cameras. Before I continue, let me take a look at the chat for questions. So Patrick says, from your tutorial, I understand that the common misconception that rasterization are better than using ray tracing in differentiable rendering. Are these reasons connected with the fact that forward rendering is slower, i.e. not real time for ray tracing? In part, they are. So going back here, at least before GPU accelerated ray tracing, we would have that rasterization can actually be faster than ray tracing based methods, at least for relatively small scenes. But as ray tracing has become faster and faster, both forward rendering and even more so differentiable rendering has actually become competitive with rasterization. In fact, an important thing is that in differentiable rendering, very often it's not necessary for us to render a derivative image that is perfect. We can very well do with derivative images that have a lot of noise and therefore can be rendered at very small sample per pixel counts at very small amounts of time. The reason for this is that we can always combine these noisy gradients with stochastic gradient descent optimization techniques that can still converge despite the fact that our gradients are imperfect in the sense that they have a lot of noise. All right. Okay. So before I go on to the second part of the tutorial, where we'll go over details for the theory of differentiable rendering using ray tracing-based techniques, I want to briefly go over a few things that differentiable rendering, and this can be either ray tracing-based or rasterization-based, does not actually give us. So things that we still need to research and investigate before we can use these techniques for different computer vision tasks. And I'll discuss this in the context of inverse rendering or analysis by synthesis applications. As Xuan mentioned earlier, differentiable rendering can also have other applications, such as integrated into neural network pipelines and so on, but I'll focus on this specific setting. So what do we mean by inverse rendering, or again, analysis by synthesis? Analysis by synthesis is the term most common in computer vision, inverse rendering the term most common in computer graphics, but they both mean the same. We simply mean that we are solving an optimization problem such as the one shown here. We're given some camera measurements of a scene. We are trying to figure out different types of scene unknowns, and we are trying to infer these unknowns by searching for the values such that when we use them to render images, we can match or we can come close to camera measurements based on loss function. And the scene unknowns, at least in the context of physics-based differentiable rendering, can be different types of physical quantities in a scene. For example, the shape or the reflectance or the scattering material of objects inside the scene, different parameters of the scene illumination, the brightness, the location, the type and environment map, and so on, and different parameters of a camera, its pose, maybe its sensitivity function, and so on. This is an optimization problem, meaning that typically a very high dimensional optimization problem, meaning that we often want to be able to solve it efficiently, we need to take advantage of gradient-based optimization. So the thing that differentiable rendering provides us in all of this picture is the small component at the bottom right. It gives us an efficient way and a general way in the context of ray tracing-based differentiable rendering to compute these gradients. All right. But to be able to successfully perform inverse rendering, there are a lot of other things in this picture that we need to be able to take care of. For example, we need to be able to take care of how to initialize our gradient-based optimization procedure. And why is initialization such a big deal? The reason is that this analysis by synthesis loss function, because it involves the rendering function, it's highly non-convex, highly nonlinear, and therefore it has a lot of local minima. And as gradient-based techniques are not global techniques, it's very easy to get trapped in these local minima. In fact, it's not just that we have multiple local minima. There are even multiple global minima, meaning that there can be different sets of parameters that can explain the images perfectly. For example, there is a lot of literature in computer vision and computer graphics, classical papers and more recent papers that describe the types of ambiguities that exist between BRDF and lighting, shape and lighting, between scattering parameters, ambiguities that show up both in direct illumination applications and in applications where we have global illumination. So to be able to avoid these kinds of local minima, convergences associated with local minima, and also ambiguities due to global minima, we need to have a good way to compute initializations for our inverse rendering procedure. And in fact, in a lot of differentiable rendering papers, you often see that differentiable rendering is used as essentially a post-processing or a refinement step, where we first have some other algorithm, say in the context of multi-view shape from motion, give us an initial estimate, and then we use differentiable rendering and inverse rendering to optimize that initial estimate. Alternatively, what we can do is that instead of using shape from motion or some other classical technique for computer vision to initialize, we may as well use a neural network or some deep learning technique to produce a first estimate that we will then refine with differentiable rendering. And these kinds of learned initializations can help us both avoid local and global minima as well as greatly accelerate the convergence of our gradient-based optimization using differentiable rendering. All right. Now, a second thing that we need to be able to determine here is the loss function that we use. Often we see inverse rendering papers, analysis by synthesis papers just use L2 losses to compare images, but there is no reason to constrain ourselves to just such simple losses. And in fact, any kind of differentiable function that can be backpropagated through can be combined with differentiable rendering pipelines to form a full end-to-end differentiable inverse rendering pipeline that can help us either reduce ambiguities that exist between parameters, or if somebody is using inverse rendering as a design task, to emphasize aspects of this design that matter the most. For example, emphasize parameters that have strong effect on perception. And for example, we can always combine inverse rendering techniques and differentiable rendering with losses based, for example, on VGG features and so on, so long as those losses remain, those perceptual losses remain differentiable. And lastly here, we need to remember that our measurements come out of a camera, which means that the measurements will be noisy, and also that we need to be able to carefully model all of the parameters of the camera that we're using to capture the images we use in our inverse rendering pipeline. And considering how nonlinear the optimization is when we're performing this type of inverse rendering tasks, the signal to noise ratio can be critical for how much we can optimize the initialization we're provided with using differentiable rendering and gradient descent based optimization. To show an extreme example, Xuan mentioned earlier a paper of ours where we are using differentiable rendering to perform non-line of sight imaging, where we are given some objects that are not directly visible to the camera. We observe them only through indirect illumination, and we're looking to recover their shapes. In simulations, using differentiable rendering can actually greatly improve upon the kind of initialization we would obtain with techniques that are not based on differentiable rendering, and recover a really very high level detail on these meshes. But when we switch to measured data, depending on the kind of SNR we have, and especially in applications such as this, where the amount of noise we have is drastic, the measurements we're working on may be just at the level of a few dozen photons, the kind of improvement that differentiable rendering will provide us with respect to some initialization may actually be minimal. And in fact, besides just dealing with noise, we need to be mindful of the fact that our measurements will be contaminated by all sorts of other non-idealities that we need to be able to model. Aberrations, electronics delays, problems in the sensor, and so on. In fact, I want to highlight here a nice paper from Kyros Koutoulakos' group where they talk about optical gradient descent. And they mention that by using a finite difference procedure, we can directly backpropagate through a camera and therefore compute gradients that accurately take into account the characteristics of the device we're using, both in terms of noise and in terms of other non-idealities that may contaminate our measurements. So, going back to this picture, these are all things to remember, that differentiable rendering is just one small part of the whole inverse rendering picture, and that there are a lot of other elements that we need to carefully design before we can successfully use differentiable rendering to perform this kind of inverse tasks. Okay, let me check for any questions in the chat. I don't see any. So with this, I'll move on, excuse me, to the second part of this tutorial, where we now start going over some of the theory that's involved in terms of how we can actually how we can do differentiable rendering, in particular physics-based differentiable rendering, and using ray tracing algorithms. And this will be the most technical part of the tutorial. We'll try to keep it at a high level, so please bear with us. Hopefully at the end, you will be able to understand some of the core challenges involved in deriving correct and efficient differentiable rendering algorithms. And we'll start by discussing differentiable rendering in the context of direct illumination. So we only care about light that only bounces a single time in the scene between the light source, some object in the scene, and then the camera. And we restrict our attention to direct illumination, both because it's an important kind of rendering problem that shows up in a lot of applications in computer vision. It's simpler than dealing with the fully general global illumination setting. And in its simplicity, it helps us draw insights about where the challenges in implementing correct differentiable rendering algorithms are coming from. Okay, now, before we actually look at differentiable rendering in the context of direct illumination, I want to make a quick reminder from stuff that most participants, most attendees hopefully have seen in calculus, in high school or in college and so on. And these have to do with differentiating simple integrals. So we have here some simple function f, one-dimensional function that we integrate between 2 points, and we want to differentiate it. To figure out how to do this differentiation, we can use a simple rule called the differentiation under the integral sign, or also known as the Leibniz integral rule. And this tells us that we can write the derivative of this integral as the sum of these 3 terms. So what do we have here? Let's break them down and look at them one by one. The first term is pretty simple. It basically says that to differentiate this integral, simply move the derivative sign inside the integral and differentiate the integrand function. But in addition to this, we have 2 more terms that show up. The first has to do with the fact that our integration limits themselves depend on the parameter pi we're differentiating with respect to. So we have some extra terms that have to account for the fact that as we change our parameter pi, the integration limits themselves change. And the third term, which is probably the trickiest one, has to do with the fact that if the function f we are integrating is discontinuous at some point, and this discontinuity depends on the parameter pi we're differentiating with respect to, we need to account for that as well. So let me show you a very simple, very quick example. We have this function f of x comma pi that is 0 for all x that are smaller than 2 pi and 1 for all x that are greater than 2 pi. We have an if statement that branches this function discontinuously into two branches. And we want to integrate this from 0 to 4 pi and then differentiate it with respect to pi. So pi shows up both in the integration limits and also in the discontinuity that appears in the definition of our function. If we apply the Leibniz rule, we end up with a derivative that has 3 terms. First, just the term corresponding to moving the derivative inside the integral. Second, a term that accounts for changes in integration limits. So here we have derivatives of 0 and 4 pi because they show up in the integration limits. And third, this discontinuity term I mentioned earlier that has to do with the fact that our function is discontinuous at the point that itself moves with respect to the parameter we're differentiating with respect to. Okay? So correctly applying the Leibniz rule, correctly differentiating this integral means that we need to account for all 3 of these terms and not simply move the derivative inside the integral. Now, going back to the Leibniz rule, we'll typically group these terms and call the first term, moving the derivative inside the integral, the interior integral, and the other 2 terms accounting for changes in integration limits and discontinuities, the boundary terms. And the reason for these names will show up in a couple of minutes when we discuss how to generalize these, how to apply this in the context of physics of direct illumination. Before we move on to direct illumination, first I want to mention that the Leibniz rule can be simplified to include just moving the derivative inside the integral when the parameter pi we're differentiating with respect to is a parameter where, when then the integration limits and the discontinuities of the integrand are independent of the parameter pi. Under these conditions, then the Leibniz rule becomes a lot simpler and is simply moving the derivative inside the integral. If these two conditions do not hold, then we need to take into account the full Leibniz rule and account for the two boundary terms I mentioned earlier. Now, all of these were for a simple integral over the real numbers. We can generalize these, and we will need this generalization when we're dealing with direct elimination, to arbitrary integrals over arbitrary domains such as hemispheres, areas, and so on. And we can do this using a theorem called the Reynolds transport theorem, which is an important result from continuum mechanics and fluid mechanics that appeared in the early 20th century. And this Reynolds transport theorem is basically a direct generalization of the Leibniz rule. It says that this derivative can be written again as the sum of two integrals, where the second integral is over a domain that includes discontinuity points in our integrand that depend on the parameter we differentiate with respect to, and the boundary of the domain that we're integrating over. Very similar to the Leibniz rule, we have a second, this boundary domain corresponds to exactly the two terms that we had in the case of the Leibniz rule. For example, if we're differentiating a simple function over an ellipsoidal domain, where we split into two halves, f equals 0, f equals 1, with a boundary that is controlled with the parameter pi, then as we differentiate, we'll end up having to include into our boundary domain this discontinuity point that depends on pi, and if it also depends on pi, the boundary of the domain omega. Same as before, we'll call these two integral the interior integral, where again, all we are doing is move our derivative inside the integral sign, and the boundary integral, where we compute additional contributions over all of these extra points corresponding to the boundary of integration domain and discontinuity points if they depend on the parameter we're differentiating with respect to. All right, before I continue, let me just check for a couple of questions in the chat. You showed an image with a scene with 34 and a link to a paper mentioned I can learn a good initialization mesh in that scenario. What is the next step after learning that good mesh initialization? What parameters and what loss functions could we use? So I'll answer this question at the end of the Q&A because it's not immediately related to what we're covering over here. So it's not to distract from the discussion, okay? All right, so going back to what we're discussing here, we saw the Reynolds transport theorem for differentiating integrals. Now, why did I bother you with all of this detail of differentiating integrals? The reason is that when we are dealing with direct illumination, and in fact, when we are dealing with any kind of radiometric quantity, at least in the context of physics-based forward and differentiable rendering, effectively what we're doing is we're computing different types of integrals. In the context of direct illumination, we will use this simple scene I show here as an example. Effectively, the intensity that our camera, the camera pointing at the point X will measure, will be an integral like the one shown here, where we are integrating over all possible directions of the unit hemisphere, the part of the sphere that is above the point X that we are looking at. And inside that integral, we are averaging incident radiance, light that this point is receiving from different light sources around the scene, weighted by the BRDF at this point, and also weighted by a foreshortening term that has to do with relative to the normal at point X. So this is a standard equation, the reflection equation, sometimes in rendering after some modifications called the rendering equation that hopefully most of the attendees should be familiar with, and it's one of the bases for physics-based vision and physics-based rendering. And in ray tracing-based techniques and physics-based rendering techniques, typically we evaluate this integral and we approximate our intensity I using Monte Carlo rendering or using Monte Carlo integration. What do I mean by that? At a high level, we start by sampling random directions omega I, so random values for the variable we're integrating over, from some PDF P of omega I. And then we form an estimator where for each one of the sampled values, we evaluate the integrand of our direct illumination integral, the reflectance, incident radiance, and shading, divided by the probability of selecting this, of sampling the specific direction omega I. Now, this is a very high level overview of how we do Monte Carlo rendering. Even just in the context of direct illumination, there are decades of research in terms of how we design the function P of omega I that we sample random directions from. But for now, this simple view of Monte Carlo rendering should be sufficient for understanding how to use all of this to do differentiable rendering. Okay. So now we want to do not direct illumination evaluations, but differentiable direct illumination evaluations. We want to take this intensity I that we've written as an integral and differentiate it with respect to some parameter pi in our C. And we'll distinguish, to see how to do this differentiation, we'll distinguish between two different types of parameters. The first is parameters that I like to refer to as local parameters, meaning that parameters that instead of affecting the entire scene, they just affect the behavior of a light ray as it interacts with just one point in a scene. And these can be BRDF parameters. So if your if your BRDF has a different albedo, a different roughness value, then these are parameters that would fall under the classification of local parameters. Shading normals, and I want to emphasize here that these are not necessarily geometric normals, the normals determined by a mesh, but normals that fake normals we attach to achieve smooth appearance, or parameters such as the brightness of some light source. So in this case, these types of parameters have the behavior, have the property that they do not introduce discontinuities into our integrand, meaning that we can do this differentiation using the simple form of the Reynolds transport theorem, or the simplified form of the generalized Leibniz rule. Just move the derivative inside the integral. Now, I want to condition my statement here that even when we're differentiating with respect to BRDF parameters or shading normals, there can be situations where these introduce discontinuities, meaning that we'll need to handle those using the more general version of differential direct illumination I'll cover in a couple of seconds. For example, if your BRDF is perfectly specular or perfectly refractive, and you are differentiating with a parameter such as refractive index, then in that case, you cannot simply move the derivative inside the integral. Or if your shading normal corresponds to very grazing angles or situations where you want to account for light leaking issues associated with shading normals, then you need to be careful, and you may need to use again the full version of the Leibniz integral theorem. But outside of these subtle and technical cases, generally for these types of parameters, expressing the differential direct illumination is as simple as just moving our derivative inside the integral for direct illumination. And correspondingly, since we have an integral, we can now do Monte Carlo differentiable rendering for this integral, meaning that we'll simply sample random directions omega I from some PDF, which may as well be the same PDF we use as to do forward direct illumination rendering, and then form an estimator that takes exactly the same form as before, except that we differentiate the numerator. So we aggregate for all of the sample directions, the derivative of the numerator, the derivative of the product between lighting and BRDF and shading, divided by our PDF. So this is the simplest version of physics-based, ray tracing-based differentiable rendering. This estimator is sometimes called the score estimator and has been around for a few years, for example, used by papers by Kungrun et al. And myself and colleagues in 2015 to solve different material inference problems. So local parameters, differential, direct elimination, simply move the derivative inside the integral. And correspondingly, in a Monte Carlo renderer, simply differentiate your numerator and divide by the sample, the PDF you use to sample directions for your estimator. There is a subtlety here that, as I mentioned earlier, there have been decades of research in Monte Carlo rendering in terms of defining the probability P that will sample directions from. And typically, this probability depends on some of the scene parameters. For example, if we limit ourselves to the case of optimizing a BRDF, typically in direct elimination, we sample directions based on the BRDF. We sample directions that will maximize the BRDF term in the direct elimination integrand. So this means that in our Monte Carlo estimation, the parameter we're differentiating with respect to, pi, shows up both in the numerator and in the denominator. In these situations, we can still apply the score estimator, where we differentiate just the numerator and ignore the denominator. But we can also take the approach where we differentiate the entire contribution. We differentiate the ratio of the contribution of a photon, or of a path, and its PDF. There are pros and cons for this. There is a nice paper in SIGGRAPH 2021 by Wenzel Jacobs group that discusses in detail the differences between these two estimators. In particular, differentiating the entire contribution can be shown to correspond to a form of the direct illumination integral called the primary sample space form of this integral that involves reparameterizing our direct illumination with respect to a set of random numbers. And it can lead to certain to acceleration or faster differentiable rendering, assuming that the sampling function you use is continuous with respect to pi. If your sampling function is discontinuous with respect to pi, the parameter we're differentiating with respect to, then doing this differentiation becomes more complicated because you need to account for the discontinuities we discussed in the context of the Reynolds transfer theorem. Okay. Now, so all of these were for what I called local parameters: BRDF, shading normals, illumination, brightness values, and so on, that allow us to simply differentiate direct illumination by moving the integral under the sign. But we can also consider, and in fact, these kinds of parameters are very actively researched and very important for many computer vision applications, parameters that I like to call global parameters. For example, the shape and pose of different scene elements, cameras, sources, objects, and so on. The difference between these global and local parameters is that when we differentiate with a parameter pi that has the form, global, that is in the form of a global parameter, we can no longer simply move the derivative inside the integral. Instead, we need to use the full Reynolds transfer theorem I mentioned earlier to do this differentiation correctly. And to highlight this and give some intuition of exactly how this works, I look again into the scene I have been drawing on the top left as my example scene for discussing direct illumination. If I take this scene and parameterize, consider how to parameterize it with respect to the size of the emitter pi. If I plot the integrand I'm computing, I see that this integrand has a discontinuity corresponding to the fact that as I look around the hemisphere, the incident illumination I have is 0 for all directions that go outside the emitter and non-zero for directions that hit the emitter. So not only is the integrand discontinuous, but the discontinuity points depend on the parameter pi that I want to differentiate with respect to. As I change the size of the emitter, the discontinuity actually changes. So what does that mean then? It means that if I want to differentiate this integral, I need to apply the full Reynolds transport theorem and end up with two terms. The interior integral, which is exactly the same as the one we discussed for local parameters, simply move the derivative inside the integration sign, below the integration sign, and a boundary integral that involves computing an additional integral over exactly the places in my hemisphere where these discontinuities show up. So these extra boundary integrals are really the key complication, the key difficulty in computing, in generalizing physics-based rendering algorithms to differentiable physics-based differentiable algorithms. And the existence of these discontinuities had been recognized a long time ago by Ravi Ramamurthy and colleagues when they were discussing analysis of direct illumination. And recently has been shown to be key for computing general differentiable and general radiometric derivatives by Jumao Li et al., something that Shuang will discuss in more detail later when he goes over global illumination. Now, to get some intuition about exactly what kinds of discontinuities we have to deal with, I'll make a small change into the way I describe direct illumination. Up until now, I describe direct illumination as a hemispherical integral. I look around the point and I go over all possible incident directions omega I at that point, and I sum up a weighted version of the incident radiance. We can rewrite this as a surface integral that says that now I integrate not over all directions, but all possible points in the scene that emit light. And this is a standard, well-known change of variables in computer graphics that results in an additional term showing up that includes visibility terms, whether a point on a light source is visible to the point x that I'm computing the intensity at, inverse square fall of terms, and additional foreshortening terms. In the context of our integration, we end up with an integrand that is a hemispherical integrand with discontinuities to an integrand that's just a surface corresponding to our light source that expands or shrinks with respect to the parameter that we're looking to differentiate with respect to the size of the emitter. And we end up going from a discontinuous integrand to a continuous integrand, but from a constant domain to an evolving domain, a domain that depends on the parameter pi with respect to which we want to compute derivatives. We can now apply the Reynolds transport theorem to either one of these versions of direct illumination. If we apply it in the hemispherical case, we see that two terms that we saw earlier. And if we apply to the area case, again, we see the two derivatives, an interior term that is simply moving the derivative inside the numerator, and a second boundary term that now involves a few, in the context of the simple scene I am showing, simply the boundaries of the emitter. But in more general scenes, it may involve discontinuities that show up in three different ways. One is boundary edges, exactly the example we saw in the past few slides, basically an emitter or some shape that has finite extent. Shape discontinuities, as we're integrating over a surface, for example, a mesh. If we have sharp edges, then those edges introduce discontinuities that as we evolve a mesh will show up into this boundary integral. And lastly, silhouette edges, effectively by switching to the version of differential illumination where we use area integration, we end up having a visibility function that changes values from 0 to 1 as we switch over the visible silhouettes in a scene. So all three of these types of discontinuities are terms that we need to take into account where we're differentiating for parameters such as shape and pose of different objects in our scene. Okay, so hopefully this have given you some intuition about the difficulties of applying differentiable rendering, physics-based differentiable rendering, which is really being able to handle all of these discontinuous terms. I want to make a few last comments before I hand it over to Xuan, where he will briefly generalize this to global illumination and also go over a few algorithms for discussing how exactly we can handle these discontinuity terms. So first, I wanted to show an example of what these derivative images look like when we do and do not take into account the boundary integral. So here we have a simple shape that we are moving vertically in this scene. If we compute the full derivative, we see, as we expect, that the top face of this shape produces a very strong gradient. If we ignore the boundary integral, we end up with a derivative image that is effectively zero everywhere. What this means is that if we compute derivatives where we are not correctly accounting for these tricky discontinuity terms, we can end up with gradients that are not only wrong, that may be completely uninformative. For example, if here I was looking to optimize for the location of this object, figure out how to move it up and down so that I can match my image, if I ignore the discontinuity terms, I will always be getting zero gradients or near zero gradients that effectively will not let me move the object anywhere. My optimization will get stuck and I will never recover the correct pose of this object. So we cannot just ignore these terms, we need to compute them, and Sai later will also show a few more examples of, for example, when we use automatic differentiation, where these terms are all completely ignored, where we can end up with catastrophic failures in optimization problems. Second, we can try and approximate these terms, for example, by smoothing out our scene, smooth the visibility, smooth the shape, and compute approximate gradients that do not actually correctly compute all of these discontinuous terms. Again, this is not as bad as completely ignoring these terms. But when we use differentiable rendering for inverse rendering applications, again, it can strongly impact the quality of the results we recover. So here I show a comparison from a paper by Xuan and colleagues that Xuan is going to talk about more later, where they optimize a shape based on some input images. And the optimization is done with a few different differentiable rendering pipelines, either based on rasterization, such as the soft rasterization, PyTorch, and NVIDIA's Diff rasterizer, or based on Monte Carlo rendering and ray tracing based techniques, such as Mitsuba 2 and the pipeline by Xuan and his colleagues. So with the exception of the Luan et al. 2021 case, all of the other are differentiable renderers that approximate these discontinuity terms, for example, by smoothing out visibility. And the consequence is that because the gradients they compute are no longer perfectly accurate, the optimization results they arrive at can be a lot worse than what you would get by correctly computing the discontinuity terms that show up in the derivative expressions. So we cannot ignore them. Our derivatives will be pretty bad. And also we can maybe be able to work with approximate versions, but it's still better if we can compute these derivatives exactly, and it can greatly improve our optimization results. And lastly, I want to mention that some of these discontinuities appear because of discontinuities or surfaces, such as boundary edges and sharp edges. But even if we are using smooth, watertight surfaces, for example, implicit representations, SDFs, occupancy functions, or neural variants of those, we still need to be mindful of discontinuity terms. In particular, even though terms due to boundary and sharp edges, terms that are driven by the topology of our surface, will no longer be applicable, we will still have discontinuities due to the discontinuous visibility function. We'll still end up with our integrals having discontinuous integrands due to visibility issues, due to visibility changing. For example, as I move an object up and down, the parts that I see behind that object will change in a discontinuous way corresponding to the silhouettes of that object that I need to take into account. So even if you are working in neural rendering and you are ray tracing implicit representations, if you want to compute accurate derivatives, you need to take into account these types of discontinuities. And in fact, I want to highlight here a very nice paper by Gargalo, Prados, and Storm back in 2007, when it was very popular in computer vision to work with implicit surfaces implemented not as neural networks, but as level sets, where they very carefully analyze all of the discontinuity effects we get due to visibilities. And they explain exactly how one needs to take into account, even in the context of just direct illumination, all of these discontinuous terms if they want to accurately differentiate images and optimize for different parameters. So with all this, I'll hand it over to Shuang, where he will go over algorithms for computing these derivative terms, and also how to generalize them to global illumination. But Shuang, before I do that, let me just check for a couple of questions that were in the chat. So Patrick earlier asked about, about a paper I showed. So here, just to be clear, I didn't mention that the initialization here is coming from a neural network. The initialization here is coming from another algorithm for no-line of sight imaging that is based on solving a linear system approximation to the image formation model. So this is a case where initialization is coming from a different technique and not a deep learning technique. So hopefully that clears the confusion. And the paper is, the specific paper is by Tsai et al. 2019 CVPR. It includes myself as a co-author. So if you Google our names, you'll find it, but we have a detailed list of references in the end. And then Donglai asks, what is the function G in the Reynolds transport theorem? So yeah, I didn't go over exactly what G involves, but in analogy to the Leibniz rule case, effectively it involves evaluations of the function f, the integrand, and also the derivative terms of that function f along the normals of the boundary. So a derivative along the boundary of a shape, or a derivative along the line that we're integrating over to account for discontinuities. Okay, so I'll hand it over to Shuang now.
Okay, thank you, Yannis. Okay, let me start sharing my screens. Okay, so Yannis has just provided a detailed explanation on how direct illumination can be differentiated and some of the challenges related to, say, handling different types of discontinuities. So what I will do next is to provide a high-level discussion on how this line of ideas can be generalized to handle global illumination. Of course, given the fact that there are lots of mathematical details involved, I will keep the discussions high level, because it's if you go into all those mathematical details, things get quite messy. So before talking about differentiation, let me first provide a high-level formulation for global illumination, which is called path integral. Keep in mind that this path integral is different from the one used in, say, quantum mechanics. It's a very different thing, happens to share the same name. So for global illumination, forward rendering, which has shown that, of course, you can model things using the rendering equation, but a different way to formulate the whole problem is that you can express the value of a pixel as a so-called path integral. So this is an integral over the path space. So path space is the set of all light paths with finite lengths. And in case of surface-only rendering, which means if we neglect all participating media, this integral will have a measure that's called area product measure, because every path vertex is over a surface. So this measure is just over each the surface area, the product of surface area measure at each path vertices. And then we have a so-called measurement contribution function that captures, for example, the light intensity, the sensor response, and all the BRDF terms, visibility. So basically it encodes everything. The benefit for having a path integral is that although it's much more complex than, say, the rendering equation, but it's an integral. It's no longer an equation. So it all boils down to basically estimating or evaluating the right-hand side. So that's pretty beneficial in terms of designing, let's say, forward rendering algorithms, since this is like a more global view of the whole problem. And this path integral formulation has then been generalized by Pauli et al. In 2000, and to also handle, say, volumetric light transport, like scattering. And as I mentioned, it can capture both surface and volumetric effects. And it has been the theoretical foundation of most modern forward rendering algorithms. And if we use the Monte Carlo integration idea, as Yannis has outlined for direct illumination, our estimator, one single sample Monte Carlo estimator typically looks like this. It becomes as simple as F over P. So you basically sample a random light path. So now it's not sampling a single direction, but an entire path. If you can do that, then you automatically get a Monte Carlo estimator that looks like this. It's basically F, the measurement contribution of the path divided by the sampling density. Of course, although the framework is simple, how to design a proper sampling process that gives you low variance is a topic that has been studied for decades in graphics, although that's not the main focus of our tutorial today. So the main take-home message here is that if you write the forward rendering problem as path integrals, then it allows one to construct estimators at such high level. We don't have to worry about, for example, the rendering equation, which you can derive estimators using the rendering equation, but it requires, say, repeatedly expanding both sides of the equation, etc., which can quickly get very messy. So the path integral formulation provides a nice theoretical foundation for the development of modern forward rendering algorithms. So speaking of path integral, we have recently introduced the theoretical formulation of differential path integral. So this is by basically differentiating a full path integral. And interestingly, we have shown that, by the way, the full derivation is quite involved, so I'm not going to cover them in this tutorial, but a high-level result is that you might find this kind of familiar with what Yannis just showed in terms of Raynaud transport theorem. So we demonstrated that even for path integrals, which are defined over this kind of very high dimensional or like infinitely high dimensional path space, you still get two terms, the interior term and the boundary term. And again, we are omitting some of the details about the exact form of the boundary term because, yeah, again, things get complicated. But only thing to remember here is that the boundary term is not hard to compute. It's not trivial to do it correctly, but once you know the right formula, the computation is not that expensive. we'll discuss how that can be done at a high level later, but here I'm just to reiterate that here we are omitting some of the low-level details, for example, on the exact form of the boundary term. Okay, so if we look at the interior integral, it's basically the same story as the direct illumination case. The interior integral is basically the same as the left-hand side with the differentiation moved inside of the integrand. So this f dot is basically df d theta, okay, in our case. And as a result, it's defined on the same path space with all this. So here omega represents the set of all light paths connecting a light source and the camera. And here the integrand f dot is basically df d theta. It's basically the derivative of the measurement contribution function f. Okay, so this is what you if you deal with local parameters, as Yannis just covered, like BRDF parameters, the interior integral might be all you get, since there's no like discontinuities that depends on your parameter. In which case, the whole problem can be handled relatively easily. However, when dealing with global parameters such as object shape, camera pose, etc., we do need the boundary term. So this is how the boundary term looks like. Again, I'm not going to go into too much details about the integrand G, but I do want to talk about the integration domain a little bit. So this domain, we call it the boundary path space. So this is the partial omega. So each element in this space is called a boundary light path. They are mostly the same as an original one, except for having exactly one boundary segment. So here, a boundary segment corresponds to one type of discontinuities that Yannis just showed. For example, the topological boundary of an object. You can have normal, like sharp edges corresponding to normal discontinuities, and of course the silhouettes, the visibility related discontinuities that you cannot easily avoid, even if you use, say, perfectly smooth and watertight shapes. Okay, I'll talk about how both terms can be estimated in the next few slides. But if we look at the problem at high level, in general, physics-based differentiable rendering requires estimating both integrals, both the interior and the boundary. So to this end, there are a number of challenges that one wants to solve. Specifically, I have listed two of them here, the two main challenges here. First one is regarding the interior integral. So differentiating f with respect to many parameters can be a challenge. We kind of already mentioned this in the introduction. And the second one is handling discontinuities, which is our main focus in this tutorial. But before diving into the details about discontinuities, let me briefly discuss the challenge regarding differentiating f with respect to many parameters. So if we look at the interior integral again, as I mentioned already, I have mentioned already, computing this f dot requires differentiating this f function, which is basically a product of all BRDFs, light emission, visibility, etc. So computing this derivative requires this big differentiation. This can be done via automatic differentiation, but there are, as I kind of again discussed briefly in the intro, we can have many path integrals to evaluate, at least one per pixel, and we have many parameters, which basically means this can result in like huge gradient matrices or compute graphs. If you do reverse mode autodiff, you can quickly make the differentiable rendering process to run out of memory, especially if you use a GPU-based version where many things are executed in parallel. But fortunately, there are specialized computational differentiation methods that are basically developed just for differentiable rendering. People have people from Wenzel Jacobs group have demonstrated that if you carefully do this computational differentiation, there are certain things that one can exploit based on the fact that we are really differentiating a light transport problem. There are better methods that can be that have been proposed so that we don't, for example, have to store full compute graphs. So we don't, and those specialized methods typically takes much less memory. So we do have solutions here, but because we have limited time, I'm not going into the details about how exactly those methods work. So now let's talk about the second challenge, which is to handle discontinuities. This basically boils down to estimating the boundary integral, which is unique to differentiable rendering. So again, here's a recap of the significance of the boundary integral. So this is the example that Yanis has shown just now. Basically, if we just neglect the boundary integral by setting it to 0, we can get very wrong derivatives that can certainly, say, break your analysis by synthesis optimization. So especially if you look at the top side of the cube, you can see if you neglect the boundary integral, you get near 0 gradient, which is not what you want. Okay, so now let me briefly introduce how discontinuities can be handled for global illumination. So the objective here is to estimate the integral over all boundary light paths. Again, as I mentioned, these are the same ones, the same as original or ordinary light paths, except for having exactly one boundary segment. So there are a number of methods that has been developed for this. The first method is called Monte Carlo edge sampling. So how it works is when you need to sample a boundary segment, because that's required when constructing a boundary light path, we can do normal, say, path tracing. And when we need to sample a boundary segment, we fix one endpoint of the boundary segment. And then we try to sample the other endpoint of the boundary segment. So this basically amounts to drawing a point from a discontinuity boundary, which can be a silhouette boundary, which can be a topological boundary, as we just discussed. Okay, so high-level idea here is really pretty straightforward. You do normal path tracing, and then whenever you need to construct a boundary segment, you do something like this. You fix one endpoint and you try to do some sort of edge sampling. And of course, after sampling the other endpoint, you still try to go back to the light source as normal ray tracing do. And again, here's a recap of the different type of edges. For example, the boundary edges, these are the topological boundaries of an object. If you have an open mesh, if you have a closed mesh, then you don't get any of these topological boundaries. And we have sharp edges. That's when you have normal discontinuities. And we have silhouette edges. This is when, say, one object occludes another object, then you get the silhouettes around the occluder, basically. And again, as Yanis mentioned, no matter how smooth your geometry is, as long as there are occlusions, you will not be able to completely avoid silhouettes. Okay, and there are, besides Monte Carlo edge sampling, there's a different method that we have introduced recently, which is called multi-directional sampling of boundary passes. So the idea, this benefits from the fact that we have a path integral formulation, because then we're allowed to construct a light path however we want. So the idea here is that we start from the boundary segment, and then we go from, we connect one end of the boundary segment to the camera and the other end to the light source. Okay, so it's kind of starting a boundary path from the middle and then kind of connecting both sides. So again, I'm staying fairly high level because many of the technical details are pretty complicated and we certainly don't have enough time for it. So these are the two solutions that I just mentioned. Solution one is the edge sampling one. Solution two is the one that I just talked about when you start from the middle. Both of these solutions can be categorized as boundary sampling differentiable rendering because we kind of deal with the boundary integral directly. There is another possibility, which is area sampling based methods, which does avoid the boundary integral altogether, but you don't do that by kind of neglecting it. You need to carefully reparameterize the original integral, and Sai will discuss this type of methods later. So in my next few slides, I will focus on the boundary sampling methods. So again, I'll keep my discussions high level, so you kind of see a flavor of how this type of methods work. When we use edge sampling, that's like a solution one. We do main path tracing as standard forward rendering. So basically, we trace a path starting from the camera randomly, of course. So we do the path tracing in the standard way. However, at every vertex, we trace so-called side passes given by a boundary segment. So for example, in the first vertex, we trace two passes, you can see, that's separated by a silhouette. That's the bottom left corner of the square, right? And then at the second vertex, we trace additional passes. And in this example, we trace a pair of passes given by the topological boundary of the light source. So again, how you get this pair of passes is based on sampling a random point along those discontinuity boundaries. Okay. So this is the first type of differentiable rendering algorithms that are capable of handling global parameters. So we didn't get this type of methods until recently in around 2018. So let me show you a simple example about how this type of method can do. So here I show a simple synthetic inverse rendering or analysis by synthesis problem. So here we have a apple-like object embedded in a rough glass cube. Because of the refraction, you can see there are multiple apples. There are also total internal reflection, which is why you see kind of apples in the other side. So here we are optimizing jointly the position of the apple and the roughness of the cube. And also the cube has some optically thin scattering media, so there are some slight subsurface scattering as well. So if we start this, you can see if we have the right gradients, then we can solve this inverse problem pretty easily. So let me show it again. So you can see the apple moves gradually to the correct location while the cube changes its roughness accordingly. Okay, so this is all kind of nice and it works well. However, this method, so the path tracing with edge sampling, has some limitations. This limitation comes from the fact that when you sample a point on the silhouette edge, it requires detecting the silhouettes in the first place. And if you have a scene with complex geometry, determining what the silhouette points are for an arbitrary surface point can be very expensive. It can be done, but even with state-of-the-art algorithm that uses like high-dimensional acceleration structures, it's still a pretty expensive process. So to avoid this, one can use the path space formulation. In this formulation, the interior and the boundary integrals are completely separated. So we're no longer doing like side passes from the intermediate vertices. Instead, we do the main path as normal forward rendering. And then we trace additional boundary passes using the multi-directional sampling process that I just showed. So basically, we start from the middle, from the boundary segment, and then go back to the camera and the light source from both ends. So this basically avoids the need of explicit silhouette detection. And another benefit for having a path-based formulation is that we can apply more advanced algorithms than unidirectional path tracing. For example, we can do bidirectional path tracing that is known to be able to handle more complex light transport effects, such as caustics. So again, I'm not going into too much details about bidirectional path tracing. But I will show a few examples where it does help. So in this one, we try to solve a inverse problem where we optimize the shape of the cross-sectional shape of a ring. So we have a ring here, as you can see from the top left rendering. We have a glossy ring lit by 4 small light sources, generating the 4 colored caustics on the ground. So here we're optimizing the cross-sectional shape of the ring so that the caustics match the target. So you can see initially the ring is very smooth, so we get very smooth caustics. The target caustics are much more complex because the target shape is much more complex as well. So if I start showing the animation of the optimization process, you can see by having a path-based algorithm, we can optimize, we can perform this type of fancy optimizations to match complex light transport effects like caustics. This even works for volumetric cases. So here we show like a comparison between the path-based method and the edge sampling method that I just described earlier. As you can see, since the path-based method allows using more advanced Monte Carlo methods, and it avoids expensive silhouette detection at the same time. So here we show like an inverse rendering comparison where 2 inverse rendering methods uses the same configurations, including initial setting and like learning rate, everything. We also keep the per iteration rendering time to be roughly the same, so equal time per iteration. As you can see, the path-based method, because of the better Monte Carlo method, because it uses better Monte Carlo method and avoids silhouette detection, it can generate much more clean gradients at equal time. So if we show how this affects the inverse iterations, you can see the path-based method converges easily, and the edge sampling one kind of gets overwhelmed by the high variance. So here we only use the image difference to drive the optimization. The parameter RMSE here is only used to demonstrate whether the optimizations have converged properly. So those are used for evaluations only. And here we show another example where we jointly optimize the shape of this bunny objects, as well as surface roughness and even optical density. So here we show like a translucent bunny with a refractive interface. We can really optimize like everything. Here you can see again how this optimization process basically applies a non-rigid deformation to the bunny model. Okay. Okay. So yeah, so this is a very high-level introduction about how state-of-the-art physics-based differentiable rendering algorithms look like when handling global illumination. So here, I think the short take-home message is that we now really can differentiate with respect to all these complex effects. You may or may not need it for your application, but the theory is there, and the systems, as we will discuss later, are kind of there also. So when you need to deal with this type of things, you might want to have a try. So okay, we do get a question. So there's a question from Patrick, saying that in the Apple example, I suppose you mean the recent demo Apple demonstrated at WWDC. The parameters optimized are position of the apple and oh, yes, I see. Sorry, I think you are referring to the Apple example that I just showed, not the WWDC Apple example. The parameters of the position of apple and the cube. Did I get it right? Yes. Okay. Let me go back to that example. Yeah, in this example, how expensive is the optimization? So yeah, we'll talk about this a little bit. In this specific example, we used a kind of proof of concept CPU-based system for everything. So it's not super fast. So each iteration takes, I think, 30 seconds or so. So it's not terribly slow, but not super fast either. And okay, how a more general question related to this, how would the algorithm work when increasing the parameters? So we're just doing normal gradient-based optimization. So we're basically computing using differentiable rendering derivatives of the loss. Finally, we're minimizing the loss, right? Here we're just using the image RMSE as our loss. So we use differentiable rendering to compute the loss, the derivative of the loss with respect to, let's say, the position of the apple, modeled as a global translation, and the roughness of the cube. Once we get the gradient, then we just do the updates the apple position using standard stochastic gradient descent. So this applies to all three examples that I just showed. We use differentiable rendering to compute the derivative of the loss, which is image RMSE, with respect to various parameters, right? And then we update those parameters using standard gradient descent process. We use Adam to drive all these optimizations. If you add rotation as well, yeah, that can be done. It doesn't change the process that much. You can, yeah, the main benefit of all these general purpose differentiable renderer is that you can literally differentiate with respect to anything. It doesn't change the how you use the differentiable renderer that much. So yes, if you want to optimize the pose of the apple modeled with the rotation, you can just add a few more parameters. How well the optimization scales to the number of parameters, that's related to one of the challenges I just mentioned, right? If you have like millions of parameters, can you run out of memory? The main issue is the memory. The forward performance is less of an issue. Of course, if you have more parameters, you have to use proper, at least reverse mode autodiff. But the main problem would be regarding scalability to many parameters is your memory. You can easily run out of memory if you don't use some of the specialized methods that I just mentioned. So this can be a problem, but we will show in the application part that we can already do pretty well when solving lots of parameters. Okay, since we don't have much time, we can certainly do more Q&A in the end. But now I will stop my sharing and I will hand over to Sai, which will cover the third option. Sai, you are muted.
Hey, can you hear me?
Yes, yep, go ahead.
Hey, so thank you, Xuan. One common feature of all of the algorithms that we've seen so far is that they generally try to estimate a boundary integral, either by explicitly finding points or by changing the domain itself to the boundary domain. So all the points you take are automatically on the boundary. Now, this usually means that these methods have two integrals over two different domains. So in this case, we're going to call that the boundary integral and the area integral. And estimating this boundary integral can have a few challenges that we don't see for the forward rendering integral. For one, since global elimination can require integrating the radians at arbitrary points in the scene, finding those edges that contribute to the derivative can require additional data structures for bookkeeping. And a particular problem for edge sampling is that edges can be occluded from vision, which can become a large problem for dense geometry where most of the edges are occluded. And we usually call this the depth complexity problem. Especially in extremely dense geometry, you see that sampling can be, edge sampling can take quite a hit. And the methods also have issues when you want to use it with perfectly specular surfaces like a mirror. So this is particularly true for edge sampling, because if you sample an edge in the scene and want to connect it through the mirror, you have to invert the mirror function. And if you imagine complicated mirrors like convex or concave mirrors, that becomes like a general function inversion problem and gets really hard. So in general, integrating our arbitrary discontinuities can be a tricky problem. Now, it's not that boundary methods can't deal with this. There's already great work towards solving these problems, but you can still wonder, is there a way to avoid having to find the samples on boundaries? Oops. So these problems motivated Loubet et al. To ask whether we can use the area samples to estimate the same quantity. Since the discontinuities are only a problem because they move when you change parameters, the idea is, why not transform the entire space to move along with the discontinuities? So their method therefore finds a transformation for the sample rays such that the movement of the discontinuities are canceled by the transformation. Unfortunately, it's hard to find this transformation that accounts for all discontinuities because it can be really complicated within a pixel. So what they do is they use a heuristic blurring approach to approximate this motion. And therefore, the method can produce bias gradients. And since we have spent quite a bit of the introduction talking about how bias gradients can cause issues for optimization, so instead, we're going to discuss another area approach that is built on the previous method that avoids discontinuities, but is also able to produce unbiased gradients. And we'll also finally see what the challenges and trade-offs are versus using boundary methods. Now, as Shuang and Yanis have already covered, but I will recap here, the correct derivative of an integral can be expressed using the Reynolds transport theorem. Essentially, the derivative of an integral is the sum of two parts. The first is an integral of the derivative defined over the interior set of continuous points. And the second component is an integral over all the discontinuous points. And this captures the contribution from the change of boundaries. Now, edge sampling tries to estimate this term by generating samples on these boundaries. And here we ask, can we estimate the same integral without having to generate such samples? In other words, can we rewrite the boundary integral into an area integral that is defined in the interior set D? For that, we look to a very old theorem called the divergence theorem, first proposed by, I think, Gauss back in the 1800s. And that states that an integral over a vector quantity over the boundary of a domain is equivalent to the integral of the divergence of the vector quantity over the interior of the domain. Now we can realize our goal of rewriting the edge integral into an area integral. It turns out that this is simply an integral over the divergence of the vector quantity, f times v. But we run into a subtle problem here. The vector v that we get from the Reynolds transport theorem is only defined on the boundary shown in blue in the illustration. That means that we must use a different quantity defined over the continuous set D, and we refer to this as the warp field v theta. But assuming that we can find such a field v theta, these two integrals are now equivalent. But the key advantage is now you can estimate this quantity using just area samples, which are usually just the rays that you use for forward rendering. Now, in order to visualize what this warp field v theta is, it's helpful to consider a simple 2D example. Consider a scene where image is simply the integral of the quantity, integral of the intensity over the domain of the semicircle centered on a camera over here. In this example, the boundary integral would be composed of the points that correspond to the silhouette of the polygon when you project it onto the camera. Now, the velocity is the rate at which these values change as the underlying scene moves with theta. If you plot these values onto a graph, you can see that this is really only defined on the set of discontinuous points, and it's undefined everywhere else because it's a quantity that is defined on boundary motion. And this is the quantity that edge and boundary sampling methods aim to compute. But remember that our goal is to compute at the equivalent area integral. So we need to find a warp field v theta defined over the entire domain and not just at the silhouette points. So what is this warp field and how to compute it? It must satisfy two conditions. The first one says that this warp field must be continuous. This is easy to see because if V is not continuous, its divergence does not exist. For example, the one on the left is continuous, while the one on the right is not. The second rule is that it must be equal to the velocity at the boundary points. That rule follows directly from the divergence theorem itself. As an example, the field on the left is boundary consistent, and this field on the right is not. If we have a field that satisfies both these rules, then our integral conversion is correct. And our problem has now been reduced to smoothly interpolating the velocity at discontinuous points to the rest of the domain. But producing that interpolation can be kind of tricky. Unlike a traditional interpolation problem, the only quantities we know about a specific ray intersection is the origin point, the ray, the intersection, and the primitive that we intersected. What we don't know are the locations of the discontinuities that can, for a mesh at least, they can be far away with and you have no information from a local intersection about where exactly they are. So our primary goal is to do this interpolation without incurring the cost of locating boundaries. Because if you could locate the boundaries, you can just use edge sampling methods and they would give you better performance. So one way to find such an interpolation is to use implicit derivatives. So we know the intersection point y is a function of both our ray direction omega and scene parameter theta. That means that the two quantities are implicitly related through the intersection function. And we can then use the derivative of omega with respect to theta just by taking the ratio of their individual derivatives. So this approach is actually also used in recent SDF rendering papers. You can differentiate the intersection point of the SDF in order to get a velocity with respect to parameters. Now, when we plot that result, we see that the warp field is by definition consistent at the boundaries. So one condition is satisfied, but it's not defined anywhere outside the surface because the intersection process does not exist for if you don't actually intersect the object. So this isn't continuous. So intuitively, let's try to think about blurring this. And that's our second attempt. We convolve the entire domain with a uniform Gaussian filter by introducing another integral. Now, predictably, the warp field is now continuous because we used a uniform blur. But a uniform blur has no guarantees on preserving this consistency at the boundary points. So at a high level, what we want to do is blur the function at the interior points while keeping the non-filtered values at the boundaries. And for this, we need boundary dependent weights that are smooth in the interior of the surface, but a sharp Dirac delta at the boundary points. Intuitively, this works because convolving a function with a Dirac delta just returns the same function. However, remember that we don't actually have access to the set of discontinuities. We can only access the current intersection point and its local geometry. So how do you compute this distance to the boundary that you need in order to apply that weighting? It turns out that you can still achieve that goal if you can instead compute some function, which we're going to call here the boundary test function, whose zero set is the set of discontinuous points. Intuitively, there's an implicit representation of the silhouette, and comes with the advantage that it's usually easier to compute compared to explicitly finding the boundary. As an example, imagine that you have a nice smooth shape. You can now use the dot product of the ray direction with the intersections normal, because conveniently, this is zero at boundaries. Now, using this idea, you can now design convolution weights based on harmonic interpolation. Harmonic weights are just the inverse of the distance between 2 points. However, instead of using just distance, we pad it with our implicit boundary function. Effectively, this means that the contribution of a boundary point approaches infinity as the sample point approaches the boundary. That weighting scheme now produces a field that is both boundary consistent and continuous. Now that we have a warp field, we need to numerically compute it. Putting all of this together, our process first uses a traditional path tracer to sample a light path. At each bounce, we sample auxiliary rays for the inner integral. We then use AutoRiff to find the implicit derivative and its weights, and then we repeat this process for each bounce. Finally, we all use all of this to compute the weighted mean and to find estimate for the warp at the current bounce. Now, we're going to quickly look at some results by using this method. When comparing against edge sampling, area methods tend to handle global illumination effects better. Here we see that edge sampling has trouble with computing the derivative of specular reflections. And that phenomenon gets worse for complicated geometry like the hedge. You can see that edge sampling just completely misses the specular reflection. By contrast, our approach avoids that problem because we use a typical path tracer and we can piggyback off of its importance sampling that is already built into the forward path tracing equation. Now, as we mentioned before, our method is an unbiased version of the other area method, reparameterization. But does this bias actually matter for our applications? So we see that by trying to optimize for a 6 degree of freedom pose estimation problem using really complex geometry, we can see that biased methods can have really badly behaved gradients that can cause the optimization to diverge completely. And this is not a one-off example. We actually verify the robustness of our method by using several different initializations, and our method converges on pretty much every initialization. Whereas using bias gradients can cause a lot of issues when you try to look at robustness. Also, you can also consider a more complicated problem of trying to estimate the pose of a corkscrew using just its shadows. The complicated geometry can make this very difficult, and you need accurate gradients to make progress beyond a certain point. You can see that it can optimize for a coarse pose, but when it comes to fine pose, bias gradients tend to have a bad time with getting that right. So to summarize this warped area sampling method, we first applied the divergence theorem to convert the edge integral to an area integral. We then derived conditions for the warp field for it to be valid. And then we described one approach to computing such a warp field using harmonic interpolation. So in doing all of this, we avoid discontinuity sampling, but at the cost of additional convolution rays for each primary ray. Now, let's change gears and take a step back. Integrating discontinuities is hard in general. And many programs and graphics actually have the same problem. We've seen that physically based rendering equation is typically an integral over discontinuities. I would actually like to draw your attention to the fact that a lot of applications actually have the same issue. They are integrals over discontinuities. That includes ray tracing, rasterization, finite element simulation, as well as physical trajectory simulation. You can think about having models that generate physical trajectories, and you would like to differentiate through them. But you end up with a very similar problem when you try to consider contact in simulation or discontinuities in finite elements. Now, Shuang and Yanis have given you an idea of just why this is a difficult task. That said, each of these domains do have some existing solutions. Like we've already seen different methods for path tracing. There are solutions for rasterization, and the same goes for differentiating physical simulation. But one issue with all of these works is that they hand-derive solutions for their fixed pipeline. And this doesn't transfer easily to different domains. For instance, you can't just take software and apply it to finite elements without doing a lot of hand derivation. It's natural to wonder then if we can automate this process. And that is actually what I'm going to be talking about now. In this work, we're going to propose a new autodiff approach for the types of integrals that we've encountered so far. But to see what's wrong with existing autodiff methods, we'll start with a small example. Let's see a very simple example where we try to compute the derivative with respect to t of an integral with a parametric discontinuity x less than t. The bracket notation here is the Iverson brackets for the indicator function. So if x less than t, the function is 1, otherwise it's 0. So to ground the problem, since it's a very simple problem, we can actually compute it on paper. We can write down the integral, and then we can differentiate it to see that it's a 3-part function, which can then be expressed using our simple indicator function. So this is the result of trying to differentiate this integral on paper. In practice, we can't compute integrals this easily on paper. So as a result, it is common to use numerical techniques like quadrature or Monte Carlo estimation. So let's first discretize the integral at a number of points, and then use automatic differentiation to differentiate each of the samples. But the derivative is 0 here. Why? Because the function is constant for all sample points. Unfortunately, that is the incorrect answer. While in general, autodiff is correct almost everywhere, this implementation does not encode the semantics of the integral. So instead, we will compute the derivative without discretizing. When you try to take this derivative, the derivative of a step function inside of an integral is 0 everywhere, except for the point itself, the point of discontinuity itself, where it becomes infinity. And this is represented by a delta function. So taken together, discretizing before you differentiate produces the incorrect result. But just differentiating the continuous integral itself produces the correct answer. Let's quickly look at this as code. Like you would want to write this down to try to differentiate this using PyTorch or TensorFlow. So discretizing involves iterating over the variable of integration. So you would likely use like a loop for this. The derivative applies to the body of the conditional, which becomes 0 here. It's necessary to have an integral primitive in order to write the code for the initial expression. And now, because we're not allowed to convert the integral to a summation, we need to keep an integral primitive to represent our derivative expression as well. But the catch here is that to handle discontinuities, you need a Dirac delta operator. But unlike other operations like addition or multiplication, the Dirac delta is really not a well-defined operation. It's literally infinity at a point. That is just one of the many reasons that make it intractable to allow them to be used as operations in programs. And so our process has a second step that eliminates delta terms to produce new delta-free expressions that we can then evaluate properly. Note here that unlike traditional autodiff, this approach gets the correct answer. But wait, how did we do this elimination step? For that, we use something called the sifting property, which is essentially just integral convolution, but specialized for the Dirac delta. The catch here is that it only applies to deltas containing a single variable of integration. That is, it has to be exactly aligned with the axis of integration. But in practical applications, that's not really true. What if we had a program that described a circular discontinuity? Maybe something like this. Formally, we say that this discontinuity is not in the normal form. And in that scenario, our system identifies and applies appropriate changes of variables to the integral domains. In this example, we could first use a polar coordinate transform, but this is still not in a normal form. So we do another reparameterization from 2r minus t to a new r prime. And this new expression is in what we call the normal form, with a single variable of integration in the delta. But we still need to convert the rest of the program to these coordinates. So the process of performing this transformation is identical. So we'll just look at the second part. Our automatic differentiation approach applies the change of variables to the bounds of integration and the delta, and then it has to substitute the old variables for the new variables using the inverse mapping. And finally, we handle the Jacobian using the derivative of this change of variables. At this point, the delta is in a single variable of integration, and we can just use the sifting property to eliminate it. So taken together, our compiler handles complex expressions like this. It first breaks down complex expressions into one piece per delta term using the linearity of differentiation. And then each term is reparameterized using a change of coordinates and subsequently eliminated to produce an expression back in the original language, and which we can now evaluate without running into issues with deltas. But what is all this useful for? So as I noted before, nearly every domain in graphics contains some form of integral estimation. Our system can automate this challenge of differentiation and provides an opportunity to revisit certain applications that were thought to be difficult to differentiate by hand. So we're going to look at a few concrete applications using our compiler. Our first application is image stylization, which is particularly relevant here since it can be solved by differentiating a rasterization function and then minimizing a loss function. Note that in order for this to work properly, we have to account for delta terms in the derivative. Starting from the same initialization, we try to optimize for a triangulated image using gradients from our method and compare it against traditional autodiff. It turns out that not accounting for delta terms in the program leads to a failed optimization. In fact, there is no gradient whatsoever because traditional autodiff differentiates only the color, and the color is constant inside each triangle. We now look at another application in noise-based shaders, which contain more complicated discontinuities. So the original Perlin noise paper proposed thresholding noise shaders as a way to design really interesting patterns. But since then, the method has seen widespread use in procedural modeling, which means differentiating this can enable exciting inverse design problems, as well as enable it to be slotted into existing differentiable renderers. So we apply our differentiation approach to a design problem where we optimize random noise to fit a certain target image. So as we show here, we can successfully solve for our design objective because our derivatives correctly account for the thresholding. But what happens if you don't? Well, like our image processing example, ignoring those terms results in different and visibly suboptimal solutions. We stress here that it is important for shaders to account for their boundary terms, because otherwise your derivatives can have the wrong sign entirely and cause your loss to completely diverge. So for our last example, we try to animate a bouncing ball between 2 points, A and B. Let's try to, usually in graphics, you would try to simulate this using a constant time step ODE, and then try to differentiate the endpoint to match point P. But if you try to do this, a ball can penetrate under the floor and result in unstable derivatives. Instead, if you're trying to differentiate hard contact, we suggest looking at a space-time constraints formulation where we parameterize the trajectory by its positions and timestamps and optimize for the Lagrangian instead. Now that allows you to handle hard contact, but the velocity in this integral is now discontinuous, which is where we need our differentiation approach. So we show here that not handling this discontinuity properly can lead to a physically incorrect trajectory, which spontaneously changes directions, in contrast to using correct derivatives where you get like consistent trajectories. So the approach we've seen here is fairly early stage. So we actually want to emphasize a few limitations, which are also potential future directions. A key requirement for the discontinuities in this ordered framework is that they must be reducible to a single variable. In our system, we provide automatic detection and change of coordinates for linear and quadratic expressions. And you can also specify your own transformations for the integrals, while our system handles all the substitutions and Jacobians. However, it's critical that the expressions have an inverse and are differentiable. So those are limitations on the expressions that we can handle. Additionally, our semantics right now only handle scalar values. So there are no indexing or tensors, and it is in an expression language. So there's no looping or recursion. Our transformation processes are also global. So this means you can't do them in modules like you can with PyTorch. And the problem can get worse when there are many, many delta terms, since the expressions can get duplicated for each term. However, we'll show that we can still apply it to practical applications in our framework section. So to give a very quick summary, we've looked at the general problem in all graphics, in a lot of graphics applications. We then proposed a new approach using Dirac deltas to account for discontinuities. That avoids the issue with traditional automatic differentiation, which discretizes first and loses the information. And because deltas cannot be evaluated meaningfully as primitives, we show that we can then eliminate these using changes of coordinates followed by sifting. So we hope that this approach provides new insights for applications that were previously thought to be too difficult to differentiate by hand. Oops, I'm actually, oh God. I'm actually going to stop for questions here. I'll answer the questions in the last section.
Okay, I think I'll take over from here. Let me start sharing my screen. Yeah, so yeah, hopefully you are not overwhelmed by some of the technical details. In fact, if you kind of have difficulties understanding some of those details, it is fine. I mean, the main objective of this tutorial is not for you to all be able to, say, re-implement all the systems that we just mentioned. So, for example, the new autodiff system that I just mentioned, I think hopefully the important take-home message that you can get there is that still boundary terms are important, as we have been like repeatedly describing in this tutorial. But there is hope that some of them at least can be handled automatically by extending the automatic differentiation frameworks that we have already been using for, say, many things. Okay, so next I will start talking about some of the systems and applications as well. I know that Sai has just covered some of them. Let me go over some, say, commonly used the differentiable renderers and some applications related to them. The first one that I should mention is Mitsuba 2. Many of you might have already know it or even tried it. So in case if you haven't used it, Mitsuba 2 is a general purpose differentiable renderer developed by Wenzel Jakob's team. It's a very feature-rich renderer. For example, it supports hyperspectral rendering, even polarized rendering. And it's also pretty efficient at handling large numbers of parameters. It has a pretty efficient autodiff library, and some of more recent, like development branch, even have the say specialized method, as I mentioned previously, that exploits the fact that we're autodiffing a light transport problem, so we don't have to store the full compute graph, for example. But currently, Mitsuba 2 has some weaknesses as well. For example, its current version only offers limited support for differentiation with respect to, say, global geometry. In fact, it only implements the reparameterization-based method that is biased, and Sai has shown a few examples demonstrating that such bias can make your optimization to diverge. So what we have been doing in our group is to develop a lighter weight general purpose differentiable renderer. So we call it PSDR CUDA. Actually, the one example that Yannis showed earlier uses this renderer. It's actually built upon the same numerical backend as Mitsuba 2. So the Inoki backend that can do efficient automatic differentiation and so on. And it also implements the path-based methods that I described when showing the CPU-based results. So one thing to notice is that this system is currently still under development. So it doesn't cover all the, say, fancy algorithms like rendering those we use to render caustics. So it's still under development. Hopefully we will get support for a wider variety of algorithms soon. So just give you an idea about how this renderer can be used. Again, it's actually similar to Mitsuba 2. You can do something like this pretty easily. So I'm just showing a short Python script. So here we can start with loading a scene. You can load a scene from a pre-specified XML file. And then you can specify, for example, if we are doing some shape optimization where we want to optimize the positions of a mesh. So you can basically set requires gradient. This basically says, okay, we take the first mesh in the scene and we want to optimize its vertex positions. And then the renderer does some, say, pre-processing, and then you can call the render function that generates the image. Okay, and then let's say we want to just minimize the image RMC, the L2 image loss. Then you can compute the loss using a standard way. So you can see the target image is an input. And then we subtract the rendered image from the target and then compute the basically RMSE, the L2 difference between the two. Since the whole process is differentiable, so you can just back propagate the loss. So in the end, you will get the gradient, which basically tells you the gradient of the vertex positions. The gradient of the loss function with respect to vertex positions. Okay, then by using this gradient, you can do, let's say, stochastic gradient descent. You can update the vertex positions using this gradient. Okay, so that's how PSDR CUDA and also Mitsuba 2 works in a very similar way. That's the interface that, say, more than differentiable renderers already support. So this is the example that I talked about earlier. So in one of our recent work, which is joint work with Fujin, Kavita, and Zhao from Facebook, we applied this system to a joint shape and material reconstruction problem. So again, we take multiple photos up to 100 of an object, and then we take some initial geometry and initial maps using standard methods like COMAP. And then we run our differentiable renderer that optimizes a loss. So to be more specific, we solve an analysis by synthesis problem, inverse rendering problem, by jointly optimizing object shape. So here we use a mesh-based representation, and also object reflectance. So this is captured with spatially varying albedo and roughness. So we have several textures to optimize as well. So as you can imagine, since we used pretty fine meshes and also high resolution maps, we get more than 1 million parameters. So that's kind of a lot, a very high dimensional optimization problem. And in this specific example, to make the optimization more robust, we used the rendering loss, as well as some regularization losses, such as mesh Laplacian and some smoothness terms that we put on the reflectance or BRDF maps. So here, as discussed earlier by Yannis, how to design a good loss is very important, but that's beyond differentiable rendering. So this is what we did for that project. And additionally, for improved robustness, we also applied a coarse to fine scheme. So we start with a coarse mesh and a low resolution maps. And after the optimization approximately converged, we kind of refine the mesh. We do a subdivision surface to refine the mesh. We also upsample the maps, and then we continue the gradient-based optimization. And another important aspect is that when we update vertex positions, we used a geometric processing library called LTOPO to avoid self-intersections. Okay, so we don't just update the vertex positions as the gradient suggests. We feed the gradient information into a geometric processing library and move each vertex maybe such slightly than the gradient specifies to avoid things like self-intersections. So we maintain a basically manifold mesh. So here is an example of the optimization process. So you can see in the initial geometry is pretty coarse. It also doesn't have any texture. So the texture is just a gray constant image. So this animation demonstrates the optimization process. So you can see the geometry is evolving. Okay. And yeah, this takes a little while to match the target, but you can see that we get lots of details and the proper reflectance information from this optimization. Okay. So here again, this is a slide that Yannis has already showed. So basically, we demonstrate in this work that the accuracy of gradients matter. So here, just to further clarify, accuracy here we mean the unbiasedness of the gradients. Remember that our gradients are estimated with Monte Carlo methods, which basically means they can have noise, but noise is fine as long as the average or the expected value matches the real, say, gradient. So again, in this result, we demonstrated that if you use approximated gradients, even if they are super clean and noise-free, you still can lose quality. For example, in Mitzvah 2, you see that it uses the approximated reparameterization, which leads to a few artifacts. The soft rasterizers, including SoftRas, PyTorch 3D, and the recent one from NVIDIA. The NVIDIA one is the most robust because it does some anti-aliasing. As I discussed very early, anti-aliasing does improve robustness. But at the very least, you kind of sacrifice sharpness of the final result. Again, all these results share the same, say, initial configuration, same learning rate, like same optimization configuration. Only thing that differs from these results is how the derivatives are, or the gradients are computed. So here we show some additional results of reconstruction, the 3D reconstruction results of real objects. Here, one thing I want to emphasize is that although we showed like normal visualization here, there's no normal mapping used here, which basically means all this detailed like normal effects, these are all geometric normals. So all these detailed geometry emerge from the underlying mesh. This kind of demonstrates the performance of say modern differentiable renderers. And because we used like mesh-based standard representations, the reconstruction results can be easily used in different applications. So here we show 2 of them. First, of course, you can import those models into like a Blender scene or any 3D modeling software so that you can model a virtual scene using them. And the second application that we demonstrated here is object insertion in augmented reality. So here we show basically the kitty model as shown here is the one that we reconstructed from a real example. So here we can easily just insert this model into a real scene. Here we used the Apple AR kit to do it. So they are kind of, because we use this standard format, the reconstruction results can be easily used in different applications. So finally, let me comment a little bit about performance. Again, this is something Yannis mentioned previously. It's actually a common misconception. So for the examples I showed just now, each inverse rendering optimization takes somewhere between 15 to 100 minutes, depending on the complexity of the target model, how many views we used, etc. However, one thing I want to emphasize here is that inverse rendering performance does not equal differentiable rendering performance. So in this specific example, differentiable rendering only accounts for less than 4% of total optimization time. On the other hand, the geometric processing part, as I mentioned, we want to avoid self-intersection and so on. These takes up to 70% of time. As you can imagine, you need this geometric processing regardless whether you use a soft rasterizer or ray tracing based system, right? If you want to avoid self-intersection, as long as you use a mesh, that's required. So what's actually the true bottleneck here is actually the geometric processing step. This is partially because the El Topo library, which is kind of state-of-the-art in this regard, is implemented not very efficiently. It's purely CPU-based and also single-threaded. So if we can improve this component, we'll get much better performance. So this, again, the take-home message here is that really differentiable rendering, even in this simple case, is not the performance bottleneck. So don't be, say, kind of afraid of using, say, ray tracing based tools at least in this type of applications. Okay, since I don't see any questions, I'll hand over to Yannis to continue the discussion. Oh, we do have a question. Okay, could it be integrated into a larger project in PyTorch? The answer is yes. In fact, all the inverse problems, the examples we showed used PyTorch's Atom to do all those implementations. Although PSDR CUDA uses a different autodiff library, it can be easily kind of connected to PyTorch. So yes, it's actually pretty easy to integrate this differentiable rendering step into PyTorch, and that's basically what we did for this very project. Okay, yeah, I'll hand over to Yannis right now.
Yeah, thanks. So I want to go over a few more applications that highlight another advantage of ray tracing based differentiable rendering, and in particular, the ability to handle global illumination. So everything I will show here are inverse rendering applications where we really need to be able to handle global illumination, and therefore the only way to approach these applications is if we use ray tracing based differentiable rendering, and in particular differentiable rendering that goes beyond the simple direct illumination models I described earlier and actually handles the full global illumination problem and the full path integral formulation that Xuan mentioned. So one of them has to do with inverse scattering. And this is arguably one of the first applications of, if not the first application of Monte Carlo differentiable rendering on an inverse rendering problem. And the idea here is that we want to reproduce the optical properties of different translucent materials, materials that have strong subsurface scattering. And this can vary from, this range from mustard, milk, shampoo, soap, wax, all sorts of liquids, and so on. Because the translucent behavior is, the translucent appearance is a result of subsurface scattering, light that goes inside these materials, inside these objects, scatters multiple times, and then emerges back towards the camera. The only way to reproduce this is, the only way to accurately figure out the optical properties controlling this translucent appearance is if we account for global illumination, and in particular, subsurface light transport. So what did we do? We built an acquisition setup that looks kind of complicated, but basically all it is that we put a sample in the middle, and then we take images of these under multiple illuminations and viewing conditions. So images look like the ones we have at the bottom right. And then once we have them, we invert these images, or rather we process these images using inverse rendering optimized with Monte Carlo differentiable rendering, in particular, a differentiable rendering implementation that includes volumetric effects. So by doing that, we can recover optical properties, scattering optical properties for all of these materials. And then once we have them available, re-render them and produce new synthetic and very realistic images of those. For example, this image that Xuan also showed earlier is rendered using scanned material parameters that we infer for different types of soap, olive oil, a type of liquor called blue curacao, or whole milk, inferred by using differentiable rendering on the types of measurements I showed earlier. Alternatively, what we can do is, this is a relatively low dimensional problem. The parameters controlling the appearance of objects such as these, objects that are homogeneous, they have the same translucent appearance everywhere. So the parameters controlling this appearance are relatively low dimensional, effectively 3 parameters controlling optical density, how often light gets absorbed, and how widely it gets scattered anytime it interacts with the material. So you can imagine that instead of having to do inverse rendering and differentiable rendering, you may just try and use some learning-based procedure to infer these parameters. Train an encoder network that takes as input images and outputs the parameters controlling translucent appearance, perhaps also with a decoder that can help make this procedure self-supervised. Even if you take this approach, there is still benefit to using differentiable rendering for this inverse scattering problem. In particular, during training, you can replace your decoder with a renderer that takes into account subsurface scattering, that takes predicted parameters and synthesize an image. And now, as you train, you can train your encoder network, the network that predicts parameters, such that it not only matches some ground truth, but also gives you parameters that can meaningfully produce the images. And adding this kind of image loss effectively provides a regularization for training our encoder, which we had found actually helps greatly improve generalization performance. Now, why do we need a differentiable renderer for this? The reason is that if we want to backpropagate an image loss between the rendered image and the input image, we need to be able to backpropagate through the renderer, and therefore we need to be able to do physically accurate ray tracing based differentiable rendering for this problem. At testing time, we don't need a differentiable renderer. We just use our trained encoder to predict material parameters. But at training time, we do use the renderer, in fact, the differentiable renderer, to try and learn the weights of this network. And just as a visualization, if we apply this kind of approach, this hybrid neural network and differentiable rendering pipeline on the problem I mentioned earlier, given one image, uncalibrated image completely even, and infer from that image the subsurface scattering parameters producing the translucent appearance of the object shown in the image, the network that is trained using rendering-based regularization can actually produce a lot more reliable predictions and much more accurately reproduce the input appearance than a standard encoder trained on the same kind of data and with the same optimization settings, but without a rendering-based regularization. So this kind of hybrid approach is something that is another use for differentiable rendering that can be applied to all sorts of inverse rendering problems. We found it to be particularly helpful for the problem of inverse scattering because in part of the fact that this is a problem, as I mentioned, where we really need global illumination, and we can only handle this global illumination using ray tracing-based differentiable rendering. Now, all of these was for, what I mentioned was so far was for homogeneous materials, meaning materials that have the same translucent appearance everywhere. But a lot of the materials around us that exhibit scattering are actually heterogeneous, meaning that they have different translucent appearance and therefore different scattering parameters, different optical properties everywhere in their interior. So this leads us to another inverse problem that we can tackle using differentiable rendering and inverse rendering called optical tomography, where we are given some translucent object, a cloud or other types of objects, and just from images taken from outside that object, we reconstruct its interior, we reconstruct its optical properties everywhere in its interior. And this is a very challenging problem for a couple of reasons. First, that again, we need to handle global illumination. Our differentiable rendering procedure needs to be able to tackle the fact that the translucent appearance we have is the effect of multiple scattering. And second, it's a very high dimensional problem. So here we are reconstructing 500,000 or 1 million density values at every voxel, corresponding to the density values at each voxel inside this material. So we have a 1 million dimensional problem where we have to do differentiable rendering to compute gradients for each one of these parameters. By using efficient differentiable rendering implementations, we can actually tackle this problem and produce reconstructions such as the one shown here, where we see a full tomographic reconstruction of a very dense smoke cloud produced only from surface measurements. And because scattering is first, as I said earlier, a great application where we need differentiable rendering that takes into account global illumination. A second, an application that is a kind of behavior that shows up in a lot of different applications: material fabrication, remote sensing, medical imaging, fabrics, industrial dispersion, and so on. There has been a lot of research and a lot of papers that focus on differentiable rendering applications specifically for the inverse scattering problem. There have been papers that use combinations of inverse rendering and differentiable rendering for different types of materials. As I mentioned, industrial materials, fabrics, clouds, and so on. Applications that use inverse rendering and differentiable rendering for material fabrication, where you are now looking to figure out not what an object is made of, but how to create an object, a heterogeneous object that has a translucent appearance. And also a lot of the recent very efficient algorithms are developed for high dimensional differentiable rendering. For example, the papers from Wenzel Jacob's group on Mitsuba 2 and radiative backpropagation have great demonstrations on these very difficult, high dimensional, nonlinear, and global illumination dependent inverse problem. Now, another problem I want to highlight, where again we have to deal with global illumination, is a type of imaging that has recently been actively researched both within computer vision and computer graphics, called non-line of sight imaging. And the idea here is that, excuse me, we are looking to reconstruct scenes, objects, BRDFs, and so on that are not directly visible to a camera and a light source. Instead, we only observe these objects from indirect reflections of those objects in some visible surface, for example, some visible wall. So in this case, the photons that leave the source will scatter on the wall, scatter on the no line of sight object, come back to the wall, and return to the camera. So our only hope in this setting to be able to see these scenes that are invisible to the camera and the light source, they're beyond the line of sight of the camera and the light source, is if we process illumination that is at least 3 bounces and above. We really, all of our signal really comes from global illumination terms. So again, this is another setting where the dominance of global illumination makes it necessary for differentiable rendering techniques to use physics-based and ray tracing-based differentiable renderers. And not only that, another reason to use ray tracing-based differentiable renderers here comes from the fact that typically this problem is a lot easier to solve by using time-of-flight measurements. And the idea here is that when we use time-of-flight measurements, if we look at any specific point on the wall and capture a corresponding histogram of photon returns as a function of time, that histogram will end up having a couple of components. A first strong peak corresponding to the surface that is immediately visible to us, and then a second very, very, very small peak, a few photons that corresponds to photons of third bounce or higher order bounces coming from the invisible object. So using this time-of-flight measurements effectively let us separate the amount of light that's coming back to us only from the non-line of sight scene from the light that comes back to us from the line of sight scene. Now, the fact that this problem is typically tackled using time-of-flight measurements means that if we want to approach this problem from an inverse rendering and differentiable rendering procedure, we need to use differentiable renderers that can actually process time-of-flight measurements. And as I mentioned earlier, ray tracing-based techniques and ray tracing-based differentiable rendering techniques can naturally take care of time-of-flight measurements. So just as a demonstration, here is a setup we built for this problem. It looks a little scary, but it's nothing else but a SPAD-based LiDAR, a LiDAR that uses a so-called single photon avalanche photodiode, a very sensitive sensor that can pick up even very weak signals consisting of a few photons. And we can now use either simulated or real time-of-flight data in this setting, together with a highly efficient differentiable renderer that can process hundreds of thousands of mesh vertices to start performing optimizations such as the one shown here, where we can take an object that is completely invisible to our camera, start from some crude initialization, in this case, some plane, and progressively optimize that using our differentiable renderer to obtain the shape of the object that we don't observe. Now, a lot of the things that Xuang mentioned earlier about shape and SVBRDF reconstruction in the line of sight also apply here. The differentiable rendering, the ray tracing-based differentiable rendering in this case, only takes about 5% of the total processing time. And a lot of the computational cost comes from the geometric operations we need to perform in order for the evolving mesh to remain free from self-intersections and have a reasonable topology and so on. So this is another instance of the application Xuang mentioned, where ray tracing is efficient, including for shape optimization, can handle very, very detailed and high dimensional shapes. And not only that, can do so while generalizing to global illumination and to cameras beyond intensity cameras, such as time-of-flight cameras. And this was a demonstration example. We can also obviously do that with measured time-of-flight data. Now, I mentioned earlier that obviously we need to be careful of the kind of SNR we have, the signal-to-noise ratio. This is even more important in this application where the non-line of sight signals we are getting are in the orders of a few photons, tens or dozens of photons. If we have a long enough exposure time for our SNR to be reliable, then we can use this differentiable rendering to greatly optimize and greatly improve the reconstructions we obtain from standard techniques such as the one shown here, where we take this bust of a horse, we hide it behind an occluder, and we observe it indirectly through some wall. We can use a technique based on a linear system formulation for line of sight imaging to get an initialization, and then greatly refine it using our differentiable renderer. And lastly, I want to mention one more case where, even though we can tackle it using just direct illumination, it is actually beneficial, or it can be beneficial, to introduce global illumination on our own. In both of the previous two settings, scattering and line of sight imaging, we had no choice but to account for global illumination. Our measurements included they were either dominated by global illumination in the case of scattering, or they consisted of only global illumination signals in the context of line of sight imaging. Here, I will talk about the application of reflectometry, where we are simply looking to measure the BRDF of some object of a known shape. This is a problem that has a very long history in computer vision and computer graphics, and typically it's tackled in a direct illumination setting, where we use a procedure called reflectometry. We take a sample of the object for which we want to measure the BRDF, and we point a light source and a camera on this sample. And as we rotate those, we measure different entries of the BRDF, effectively different values of the BRDF at different incident and outgoing directions. And if we do that for material samples that are, for example, a sphere or a planar surface and so on, effectively all of the measurements we have are direct illumination measurements, meaning that we can directly map our intensities to values of the BRDF. This is nice in the sense that it's computationally tractable. There is no inverse problem to solve, but it comes with a high cost on the acquisition side. We need to take many, many measurements of this sample to be able to densely sample our BRDF. Effectively, we need to do a 2D scan of our light and camera around our material sample to be able to figure out the BRDF. What we can do now is, instead of rely on direct illumination measurements, change the shape of our sample so that now our measurements will include global illumination. For example, in the simple example I'm showing here, instead of taking a spherical sample of the unknown BRDF or a convex spherical sample of the unknown BRDF, we can take a concave sample. And now, in addition to the measurements we have from direct illumination, our images will include a lot of photons that bounce multiple times inside our sample. And all of those effectively give us measurements that sample the BRDF at a lot more pairs of incident and outgoing directions. So by inducing global illumination artificially, we can greatly reduce the number of measurements that we need to take in order to have a dense sampling of the BRDF. In fact, we can get it down to a single image for densely measuring this for the BRDF. The downside of this approach, of course, is that now, because we have global illumination, we can no longer map intensities directly to BRDF values, and we have to do analysis by sequence optimization. In fact, before the emergence of general purpose physics-based differentiable rendering algorithms, this was an intractable problem, and therefore this was a procedure that researchers typically avoided. But using the now available differentiable renderers, we can now start tackling this problem and exploring different ways to perform reflectometry in a way that is very efficiently acquisition-wise. So just for a quick visualization, we can take a shape that is either a convex or a concave sphere and visualize, using the bivariate representation of a BRDF, exactly what entries we sample in this BRDF using paths of different orders. For example, if we use just single bounce paths, we only sample a specific row in the bivariate representation of a BRDF corresponding to a fixed difference angle and different half vectors. And then as we consider two bounds or even higher bounds paths, all bounds paths, we see that whereas obviously in the convex case, we have only direct illumination, our BRDF sampling remains the same. In the concave case, where we now take into account global illumination, we end up with measurements that include very, very, very dense samples of the BRDF at most difference and half vector angles. And if we start doing inverse rendering in this case, we can see that on the basis of the same number of measurements, because of this much denser sampling, we can get a lot more accurate BRDF reconstructions than we could with just using direct illumination and just a single image. Or put another way, if we wanted to get the same kind of accuracy in the BRDF reconstruction in a direct only illumination case, would have needed to take a lot more measurements because of the fact that direct illumination gives us a very sparse sampling of the BRDF. Not only that, but we can now start asking questions such as, of all of the possible shapes that induce global illumination for this problem, which one is the optimal one for BRDF reconstruction? Which one gives me, in a single image, the densest possible sampling for BRDF? And in our paper, this is all work that we did with Sai here, Kafir Semtov, and Anat Levin presented in ICCP 2020. We saw a procedure for discussing an optimized shape, I wouldn't say optimal, for BRDF reconstruction from interreflections. And in fact, we show that in all of these cases, the single image acquisition that takes advantage of global illumination can give us an order of magnitude improvement in terms of the quality of BRDF reconstruction. So I wanted to close with one last note regarding global illumination. So as I said earlier, traditionally in computer vision, we have been avoiding global illumination because we could not handle it. We didn't have inverse rendering pipelines, and we didn't have differentiable rendering pipelines that could actually manage to differentiate scenes that include global illumination effects. The fact that we now have these available allows us both to greatly extend the application domains where we can apply inverse rendering, and I mentioned as a couple of examples, inverse scattering and all line of sight imaging. But it also allows us to, or maybe should motivate us to go back and rethink about some of the some classical problems that in computer vision we have approached only within the constraints of direct illumination. For example, maybe rethink acquisition systems so that we can improve them to take advantage of global illumination, like I said, in the context of reflectometry, or even revisit theoretical problems that previously were constrained only in the direct illumination setting because that was the only setting we could computationally tackle. For example, at the start of the first part of my presentation, I mentioned different classical results in computer vision about uniqueness of BRDF shapes and materials. Illumination can produce different images. All of those results typically assume direct only illumination and examine ambiguities that exist between those parameters if we only take into account direct illumination. Now that we can tackle versions of those problems that have global illumination, we can go back and also revisit these theory problems and examine whether these ambiguities go away when somebody takes measurements where we have intentionally introduced global illumination. And in fact, I want to mention here that one of arguably one of the earliest differentiable rendering papers in computer vision was in the 1990 by Sri Nair and his collaborators on shape from interreflections, a paper that won the Marr Prize at ICCV 1990, where they said that using a differentiable renderer based on radiosity techniques, we can produce reconstructions of diffuse shapes even in the presence of interreflections. Later work has shown that this may be useful not just for situations where we simply cannot handle the fact that our shape is concave and therefore we have interreflections, but it can also help reduce some of the classical ambiguities that exist when people do shape from shading and photometric stereo for diffuse surfaces. In particular, Manmohan Chandrakar and his colleagues showed that this being able to handle global illumination removes the generalized bas relief ambiguity that exists when we're trying to recover shape under diffuse shape under a non-illumination. So that's all I had to show. I put together a list of references for all of the papers that we mentioned, Shuang, Sai, and I, during this presentation. Obviously, we cannot go through all of them right now, but since this video will be posted on YouTube, you can pause and look at the different papers. So papers on theory and algorithms of differentiable rendering, systems and applications, so Redner, Mitsuba, PSDR, TEG, and the different applications I mentioned, as well as a few other of the papers I mentioned during, all of us mentioned during our discussion. So with that, I'll hand it over to Shuang.
Yeah, before I give the high-level summary, maybe Sai wants to talk very briefly about Retina first.
Hey. Yeah, so I want to give a very quick, brief summary of one of our frameworks, Redner. Okay. So Redner was actually a sort of a predecessor to PSDR. It was introduced with the first boundary differentiable rendering algorithm by Lee. And Shuang and Yanis have already covered the algorithm itself. I just want to look at the framework, the goals of the framework. It's built from the ground up for ML applications. You can slot it in as a layer inside your rendering model, and it will you can call it backward on it, and it will automatically produce derivatives of shapes, light, camera position, etc. Now, Shuang and Yanis have already covered the features of a physically based differentiable renderer. Redner is also based on this, but it doesn't use the path space formulation. Instead, it uses edge sampling, so it's usually better for primary visibility. I just want to cover a few extra features outside of physically based rendering that could be useful. For one, if physical rendering is not your goal, Redner also supports deferred rendering. It renders out something like G buffers. These are essentially some things like positions, normals, albedo, etc. You can then combine these to produce post-process lighting like that of Softras and PyTorch 3D. But the difference is that you can get accurate gradients because of the edge sampling. And one other update is that in the latest update, Redner's experimental branch now contains both edge sampling and the warp field method. So you can pick and choose which one you want and get the benefits of both. We provide an easy way to swap between the two methods. You just have to change one line, and you can choose which one you want based on the current requirement. As a general rule of thumb, edge sampling works great for primary visibility, while warp sampling works better for higher order illumination, like reflections. Now, as someone asked in the chat, you can use Redner or PSDR CUDA anywhere in your differentiable rendering pipeline. For instance, you can use it to optimize or train morphable models. This is an example of using a 3D face model, and you can train for its parameters to optimize for a target image. You can also use it at the input to find adversarial examples for a classifier network. For instance, in this example, we train a stop sign until VGG, the VGG network classifies it as a handrail instead of a stop sign. Alternatively, you can also use it to optimize for fine-grained posts. You can use the output from a different method as initialization, and then use Redner or PSDR CUDA to do the final optimization. Of course, this is not specific to Redner. Other differentiable rendering frameworks can also be slotted over here. And you can do so much more with a differentiable rendering layer. So try Redner out today at the following links. Redner is GPU accelerated through NVIDIA Optics. It's available on all 3 platforms, and you can install it using pip. Alternatively, you can run it right now on the cloud, even on your phone. And the bottom right links to an IPython notebook with a live example of pose optimization using edge sampling. Thank you. I'm going to hand it to Shuang now.
Thank you. So yeah, since we are running out of time, let me make the final summary. Screen. So, okay. So we have talked about a fair wide array of aspects regarding physics-based differentiable rendering. So the technical part might be a little too dense, but hopefully you get the following, say, take-home messages. So first, we have shown that great progress has been made in the field of physics-based differentiable rendering. So now, specifically now, say modern methods are capable of handling global illumination and say differentiating with respect to scene geometry with decent efficiency. We have talked about systems like Retina, like PSDR CUDA, Mitsuba, and also the new automatic differentiation framework. So although most of them are still kind of under development, I wouldn't say any of them are kind of super polished, ready for product. But if you have a research project that may need differentiable rendering, trying some of them might be a good idea. And also, this is a point that have been made multiple times. Ray tracing is no longer slow thanks to, for example, RTX, the hardware support and everything. And beyond that, as Yannis and I have demonstrated in multiple situations, when solving an analysis by synthesis problem, very often, of course, it depends, but very often differentiable rendering is not the performance bottleneck. So you have other things like back propagating your loss through a huge computer graph. You have like geometric processing if you use a mesh-based formulation. All these operations are actually way more expensive. So you really shouldn't be, say, scared of using ray tracing because it's kind of slow by the internet. And also have demonstrated that gradient accuracy matters. Yes, you can approximate gradients, visibility gradients in certain ways, but be aware that there might be a price to pay in terms of reconstruction quality. And then lastly, discontinuities always exist as long as you have occlusion, you have something occluding another thing or self-occlusion, then discontinuities always exist regardless how smooth your surface is. And related to these discontinuities, if you take traditional automatic differentiation and apply that to a path tracer or many other pipelines, it might not work because traditional automatic differentiation really neglect all discontinuity boundaries. Okay, so yeah, we would like to thank all our funding agencies and thank you for your attention. And we have a tutorial website shown in the QR code. We will have the tutorial materials there and also the, for example, the references that Yannis just showed will also be available there. So now, yeah, now we are happy to take, I know we are a bit over time, but if you have any questions, please feel free to ask in chat. We do get one. Does radiative backpropagation make it faster or at least more direct? Radiative backpropagation tackles the problem of you need a very big computer graph to get the interior integral differentiated mostly. So if you use radiative backpropagation, you can use much smaller compute graphs and thus gets better performance and lowers the memory consumption. So that's the main kind of practical advantage offered by radiative backpropagation. So yeah, but it's a specialized technique. So it's specialized to differentiating the kind of the rendering equation. So if you have a different application, it might not work. Okay, is there any other questions? Yeah, okay. If that,
we also covered all of the questions that were asked earlier, right? During the presentation.
I think so. Please remind us if your question is missed. Does PSDR have correct limits in number of image of resolution? Yes, this applies even to forward rendering. So basically, as long as you do GPU-based rendering, you kind of paralyze the evaluation of every pixel. So even, yes, so if you have a super high resolution image, it can run out of memory because you have to store everything kind of during those parallel computations. With that being said, you could, for example, break a big image into smaller image blocks and then render them, maybe do some mini batch thing to randomly pick a few image blocks. So yeah, there are so the short answer is yes, because of the GPU framework and the need to parallelize kind of pixel level computations. Even forward rendering can run into memory issues, let alone differentiable rendering. But on the other hand, there are methods like you do some mini batch and other things that can be used to mitigate this type of problems.
Specifically regarding the number of images, a common trick is to effectively use mini batch at every gradient. So instead of optimize your loss for all images, you can sample some of those images and just compute gradients with respect to that smaller number of sampled images.
Yeah.
Because I mentioned is effectively a version of mini batching during gradient descent.
Yeah, you can do mini batching at the image level or even within an image. If you have super high res ones, you can render part of the image. Yeah, but again, it all boils down to mini batching in stochastic gradient descent. Okay, yeah, if there's no more questions, I think we can conclude here. And as I mentioned, we will have the course recording and like the course materials available on the tutorial website. So feel free to check for those materials. And if you have any more questions, feel free to contact us, and we're happy to discuss, for example, potential use of these modern differentiable rendering techniques. Okay, thank you. Hope you enjoyed the course.
Thank you, everybody.
Thank you.